Welcome, curious minds and sleepy thinkers. You found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. As the day's hustle melts away and shadows lengthen softly around us, let's allow our thoughts to drift beyond the familiar ceiling above, past the clouds, and into the cosmic expanse. Tonight we're going to tiptoe into one of the most profound and perhaps most humbling mysteries of all, the vast, vibrant home we call the Milky Way galaxy. It's a place we inhabit, a cosmic island we drift upon, yet in many ways it remains as elusive and enigmatic as a dream whispered just before waking. But don't worry, we'll take it slow. This isn't a race through equations or a lecture filled with hard facts to remember. It's more like floating gently on a calm moonlit sea, allowing the currents of wonder to carry us through a galaxy of ideas, perhaps with a warm cup of chamomile tea cradled in our hands. We'll explore what we know, and more beautifully, what we still don't know, allowing the vastness to soothe rather than overwhelm. Are you ready to begin our quiet journey? Imagine for a moment that you live inside a magnificent, sprawling city. A city so vast that its edges fade into perpetual twilight and its tallest spires touch realms unknown. You've spent your entire life within its gentle embrace, breathing its air, feeling its rhythms, yet you've never truly seen its full silhouette, never counted its buildings, never quite grasped its true form. This is our quiet predicament with the Milky Way, our galactic home. It's a paradox, isn't it, to dwell within something so grand, so fundamental to our existence, and yet to understand so little of its basic nature. We are, in essence, trying to draw a map of our own house from the inside, with the walls and rooms themselves obscuring the grander design. This humbling mystery begins with perhaps the most fundamental question of all. How many stars are truly twinkling within our Milky Way? The numbers tossed around are not a whisper, but a vast, shimmering range stretching from 100 billion to a breathtaking 400 billion. Think of this as trying to count grains of sand on an endless beach while standing right in the middle of it. Each grain a sun, a system, a potential story. The very spread of these estimates, so wide and encompassing, speaks to the immense challenge of even the most basic senses. Are we looking at a bustling metropolis with 250 billion inhabitants, or a more sparsely populated, though still overwhelmingly grand cosmic town? The truth remains elusive, a number known only to the universe itself, whispered on the solar winds. And then our celestial home reveals another layer of its mystery, its very shape. When we picture other spiral galaxies, we see them from the outside, like glittering cosmic pinwheels, their graceful arms unfurling into the dark. But what of our own? Does its spiral boast 2 grand sweeping arms, or 4 like an elegant cosmic embrace? For decades, scientists, like diligent detectives, have been leaning first one way, then another, their theories shifting like sand dunes in a gentle breeze. Currently, the whisper in the scientific community suggests 4A, more intricate, complex dance. Yet, it's not a certainty carved in stone, but a leaning, a prevailing hunch. It's a testament to the fact that sometimes the simplest questions about our immediate surroundings are the hardest to answer, precisely because we are so deeply embedded within them. Imagine trying to discern the exact pattern of a kaleidoscope from a single shard of colored glass, rather than looking at the whole ever-changing mosaic. We see glimpses, fragments, the light from distant stellar nurseries filtering through the cosmic dust. But the overarching design, the full majestic sweep of our galaxy's arms, remains a grand, elusive secret. The shifting theories remind us that even in the vastness of space, humility is our constant companion. The universe doesn't readily give up its secrets even to its diligent observers residing within. It asks us to be patient, to be curious, and to always be ready to adjust our understanding as new whispers of data reach us. This inherent difficulty of peering outward from within is not merely a poetic thought, but a tangible challenge that astronomers grapple with every waking moment. It is easier, certainly, to gaze out your window and admire the house across the street, to map its eaves and count its windows than it is to stand in your living room and visualize the exact dimensions and layout of your own roof or the curve of your own driveway. The very substance of our cosmic home, the stars that illuminate our night, the swirling clouds of gas and dust that cradle new suns. These are the very elements that weave the veil between us and a clear panoramic view of our galaxy. They are beautiful, yes, but they also serve as cosmic curtains, gently obscuring the grand theater beyond. Think of trying to understand a vast forest while lost deep within its ancient trees. Each towering trunk, each dense canopy, while magnificent in itself, contributes to the beautiful, bewildering maze. We can glimpse shafts of light and hear the rustle of leaves, but seeing the forest from above, understanding its true boundaries, its winding paths, or the spread of its individual groves, remains an impossible task from the ground. So, it is with our Milky Way. Every star we cherish, every nebula that paints the night sky with vibrant hues, every wisp of cosmic gas, all these magnificent components in their sheer abundance become part of the very obstacle to our comprehension. They are the beautiful glittering fog that surrounds us, enchanting, yet confounding. And nowhere does this challenge become more profound, more beautifully frustrating, than when we attempt to gaze towards the very heart of our galactic home. This region, teeming with the greatest concentration of matter of stars and dust and gas, creates what astronomers affectionately, yet somewhat despairingly, refer to as the zone of avoidance. Imagine a dense ancient fog that rolls in thick and impenetrable precisely over the most magnificent part of our cosmic city center. Visible light, the very medium through which we typically perceive the universe, struggles to pierce this cosmic shroud. It is absorbed, scattered, and utterly lost in the dense, swirling maelstrom of matter. So, like explorers seeking a hidden path, scientists must resort to other senses, other ways of seeing. They turn their gaze to mediums that are less easily deterred, like the penetrating whispers of X-rays or the deep hum of infrared light. These different wavelengths of the electromagnetic spectrum become our intrepid guides, slipping through the cosmic fog where visible light simply bounces back. It's like trying to navigate a dense jungle in the dark and suddenly discovering that a special pair of goggles allows you to see the faint heat signatures of life moving through the undergrowth. This shift in perspective, this change in our cosmic eyes, allows us to begin scrutinizing what lies beyond the visible to dimly perceive the true bustling heart of our home. Yet it remains an indirect view, a shadowy outline rather than a clear luminous portrait. The zone persists a reminder of the universe's exquisite ability to hold its secrets close, and the house analogy, our quiet meditation on our galactic home, can truly deepen here. We are in a very real sense sitting in our bedroom, perhaps by a window, trying to decipher the layout of the grand mansion we inhabit. But the sturdy walls right in front of us, those made of cosmic dust and countless stars, prevent us from seeing the other rooms, the other walls, the sprawling corridors that connect our chamber to the rest of the house. We know they exist. We sense their presence, perhaps even feel their subtle gravitational pull. But their exact configuration, their true dimensions, remain veiled. This beautiful, frustrating proximity creates a unique challenge. Unlike mapping a distant city from afar where its entire form can be observed, we are immersed in our subject, its very essence becoming the greatest barrier to its holistic understanding. Adding another layer to this cosmic puzzle is the fundamental difficulty in truly knowing how far away a star is from our vantage point here on Earth. Imagine looking at two distant lights in the night, one a small dim candle close by, and the other a roaring bonfire far, far away. Without any other information, how could we truly tell which is which? This is the celestial dilemma that confounds our attempts to create an accurate 3D map of our Milky Way. We need to know if the stars that sparkle faintly in our telescopes are truly dim small and therefore close companions, or if they are in fact colossal, brilliantly luminous giants whose light has been so diminished by the vast cosmic distances that they only appear dim and small to our earthly eyes. This ambiguity is like trying to sketch a landscape where every tree could be either a sapling or an ancient redwood, merely scaled by distance. Not all stars thankfully conspire to make this task an insurmountable one. Some celestial beacons, like the wondrous Cepheid variable stars, offer us a rare glimpse of predictability in the cosmic chaos. These are like cosmic lighthouses, their rhythmic brightening and dimming, following a precise pattern, a kind of celestial heartbeat. What makes them so incredibly valuable, these cosmic yardsticks, is that their pulsation period, the time it takes for them to go from bright to dim and back again, is directly linked to their intrinsic luminosity, their true inherent brightness. If you know how truly bright a Cepheid is, and you can measure how bright it appears to be from Earth, then the simple laws of light and distance allow you to calculate its cosmic address to pinpoint its location on our galactic map with surprising accuracy. Imagine holding a light bulb in your hand, knowing its wattage, its true brightness. If you then see the same light bulb shimmering faintly far across a field, you can, with a little calculation, determine just how far away it truly is. The Cepheids offer us the same elegant solution on a grand cosmic scale. They are the stepping stones, the reliable markers that allow us to begin building a more precise understanding of the vast distances within our galaxy and even beyond. However, the universe in its infinite wisdom does not make all its stars quite so accommodating. Many indeed, most stars do not possess this predictable luminosity. They burn steadily, or flicker irregularly, or simply do not offer us such a clear inherent measure of their true brightness. For these unpredictable stars, these countless individual sparks scattered across the cosmic canvas, how then can we hope to fathom their distance, to place them accurately on our ever-growing map of the Milky Way? This question leads us to a principle that surprisingly is as simple and as ancient as closing one eye. The answer, my sleepy thinkers, lies in something called parallax, and it is this very principle that the magnificent Gaia Space Telescope, our diligent cartographer in the sky, has been so patiently employing over the last decade to build its breathtakingly detailed map of our galaxy. Parallax at its heart is a deceptively simple concept, the apparent shift in the position of an object when viewed from different vantage points. It's a phenomenon we encounter every single day, often without even noticing its profound implications for understanding the universe. You can right now experience this gentle cosmic dance for yourself. Hold your finger up in front of your face, about arm's length away. Now close one eye. Then instead, gently close the other. And now try alternating quickly between the two, watching your finger. Do you see it? Your finger appears to leap to shift quite significantly against the distant backdrop of your room. That little jump, that apparent movement, is parallax in action. It's a whisper of how the universe reveals its depths. The closer an object is to you, the more pronounced, the more dramatic this effect of parallax will be. Your finger so near seems to dance quite widely. But if you were to look at a distant tree on the other side of a sprawling field and repeat the same eye-closing exercise, the tree's apparent shift against the far-off horizon would be much, much smaller, almost imperceptible. This simple observation holds a profound truth for the cosmos. The further away something is, the harder it is to use parallax to tell you its distance. The celestial dance becomes so subtle, so minute, that our measurements can become a little imprecise, a little blurry at the edges. But how then can we possibly apply this simple finger and eye trick to the incomprehensibly vast distances of a star? Our eyes are but mere centimeters apart, a tiny baseline for such cosmic measurements. The secret. The elegant solution to this cosmic scale problem is to widen our base viewpoint, to extend our cosmic eyes across a far greater expanse. Just as the distance between your two eyes influences the perceived shift of your fingers, so, 2 does a larger separation in our observation points unlock the distances to the distant suns. Gaia, in its patient, unwavering vigil, did not simply glance at stars once, but meticulously observed them multiple times over the course of a full decade. Think of it as taking countless photographs of the same twinkling star from slightly different positions as we, the Earth, embark on our grand orbital journey around the Sun. Over that span of time, the face of our night sky, while seemingly immutable to our fleeting human gaze, will have ever so subtly changed. We see this beautifully illustrated in time-lapse images where the stars appear to trace little looping patterns across the celestial sphere. This isn't, of course, the stars themselves whimsically dancing in circles. It is a reflection of our own planet's grand annual loop around our Sun. Rather than relying on the mere 6 centimeters that separate our eyes as a baseline every half year, we can, in essence, make our entire solar system our new expansive baseline. As our Earth gracefully moves from one side of the Sun to the other in its stately annual orbit, a tiny yet measurable parallax effect becomes visible in every star we observe. It is this gentle cosmic sway, this yearly wobble in a star's apparent position, that Gaia so meticulously captures. Each tiny loop, each subtle shift is a whisper of distance, a clue to its true cosmic address. Yet even this vast orbital dance of our planet is not the grandest stage upon which to measure parallax. There is an even larger scale, a more profound motion we can tap into to deepen our understanding of stellar distances. This involves what astronomers call the proper motion of stars. Here we can even set aside the tiny annual loops caused by Earth's orbit, for a far grander baseline comes into play. It is not just our planet that is in motion. Our entire solar system, along with countless other stars within our galaxy, is also embarked on its own majestic journey, sweeping through the cosmos. So we can leverage this vast collective motion, this grand galactic drift, as an even more expansive baseline for establishing parallax. The fundamental principle remains the same: stars that exhibit a more pronounced proper motion, a more noticeable apparent movement, against the distant unchanging backdrop of space, are by their very nature closer to us. Conversely, those stars that show less proper motion, remaining more steadfast in their distant glimmer, are indeed further away. It's like watching 2 boats on a distant ocean from a moving ship. The nearby boat will appear to shift more dramatically against the distant horizon than the one far away. In this meticulous, painstaking manner, observing billions of stellar shifts and dances, Gaia has been diligently building its precise 3D map of 2 billion stars within our own Milky Way galaxy, and even venturing a little beyond its immediate embrace. This monumental undertaking, spanning a decade and encompassing a staggering 3 trillion observations, is a testament to the power of patient, persistent observation. Each captured photon, each measured shift, contributes to an ever clearer, ever more detailed portrait of our galactic home, revealing its hidden depths and the true intricate ballet of its countless inhabitants. It is a slow quiet, unveiling a cosmic cartography drawn with light and time, beyond simply charting their movements and distances. Gaia, our gentle cosmic cartographer, extended its gaze to understand the very essence of these celestial travelers. Imagine not just knowing where someone lives and how they move through a city, but also understanding their inner workings, their warmth, their unique glow, their very composition, and how much substance they hold. This is what Gaia has achieved for billions of stars, delving into their luminosity, their temperature, their mass, and their chemical makeup. It's a deep personal inquiry into the heart of each individual sun, painting a portrait far richer than mere location could ever convey. To achieve such an intimate understanding, Gaia was equipped with senses far beyond our own. It housed 2 powerful telescopes, like twin eyes, each channeling light from different directions onto a single extraordinary camera. This wasn't just any camera. With nearly 1 billion pixels, it holds the distinction of being the most precise camera ever sent into the silent, cold expanse of space. Think of it as a painter's brush, capable of capturing the most subtle variations in color and light, allowing astronomers to discern the faintest blushes of warmth or the most intense flares of brilliance from stars light years away. Every photon, every tiny packet of light captured, became a piece of a grand cosmic mosaic revealing the hidden characteristics of these distant suns. Among its sophisticated instruments was the radial velocity spectrometer. This remarkable device, like a sensitive ear, listening for a faint echo, measured something called the Doppler shift. Imagine a police siren, its pitch changing as it approaches you and then recedes. That change in pitch, that alteration in sound waves, is a form of Doppler shift. In the cosmos, light waves behave similarly. As a star moves towards or away from us, the light it emits shifts slightly in its wavelength. A subtle blue shift if it's approaching, a gentle red shift if it's receding. By meticulously measuring these minuscule shifts, Gaia's spectrometer could give us precious clues about a star's velocity, its speed and direction of travel directly towards or away from us. It's like feeling the pulse of a star, understanding the beat of its journey through space. Then there were the photometric instruments, which acted like a discerning eye for color. These weren't just about capturing a pretty picture. They were designed to reveal the spectral information about each star's properties, like its chemical composition and its precise temperature. Imagine analyzing the unique fingerprint of light that each star leaves behind. Just as a human fingerprint reveals individual traits, a star's spectrum reveals the elements it's made of and how hot its surface burns. A star blazing fiercely with blue light whispers of immense heat and youth, while a cooler, more sedate star glowing faintly red speaks of age and gentle energy. Together, these instruments allowed Gaia to build a comprehensive dossier for each of the 2 billion stars it observed, transforming distant points of light into richly understood celestial bodies. It's a humbling thought, isn't it? 2 billion stars, a number so vast it stretches the imagination. Yet when we consider the estimated 100 to 400 billion stars thought to reside within our Milky Way, those 2 billion stars are in truth but a mere drop in the cosmic ocean, a single shimmering tear in a vast, glittering sea. And yet, this seemingly small fraction has allowed us to create an incredibly detailed map of our galaxy, one that continues to deepen our understanding with every new piece of data. It's like drawing a map of a boundless forest by meticulously charting every leaf and branch of a single, majestic grove. While it doesn't cover every tree, it provides an unprecedented level of detail for the trees. It does encompass, allowing us to infer patterns and structures for the forest as a whole. And it is precisely that over-time aspect of Gaia's mission that has allowed us to uncover some of the Milky Way's most astonishing, even ravenous habits. For since its launch in 2013, Gaia has been patiently collecting data, a steady stream of cosmic whispers. This colossal trove of information has been processed by ESA scientists and then with generous wisdom released in large data packets for the general scientific community to pore over, to analyze, to dream with. It's like opening a vast ancient library filled with scrolls of celestial secrets, inviting every curious mind to decipher their meaning. The longer the gap in time between these observations, the more comprehensive and precise the data becomes. Think of taking repeated measurements of a flowing river. The more times you measure, the more accurately you can chart its currents, its eddies, its true evolving path. More time in Gaia's case simply translates to more parallax and thus more accurate distance measurements, allowing for a more profound understanding of stellar motions. So far, 3 such grand data releases have graced our scientific community. The first, a gentle whisper of discovery, arrived in 2016. The second, a louder, more confident announcement in 2018. And then a grand 2-parter, releasing a simplified version in 2020, followed by the full intricate tapestry in 2022. Each release a new chapter in our unfolding understanding of the cosmos. And with each new chapter, scientists have had the profound opportunity to evaluate what Gaia has so patiently observed. As they witnessed the subtle motions and precise locations of stars within our galaxy unfolding over time, a magnificent possibility emerged. It became possible to model the whole galaxy, to construct a digital twin of our cosmic home, and even with a sense of playful cosmic magic, to wind it backward. Imagine a celestial clock, its hands moving not forward into the future, but backward through eons, revealing the ancient dances and dramatic collisions that shaped our present. Look at this, if you will, through the mind's eye. While it's impossible to photograph our own galaxy from the outside, no camera-equipped spacecraft has yet ventured far enough into the cosmic ocean to capture such a panoramic view. What we can see is a representation, a breathtaking visualization created entirely from Gaia's data, revealing what our Milky Way truly looks like to an unprecedented degree of accuracy. It's not a photograph, but a true portrait meticulously rendered from billions of data points. And as you behold it, you might notice something peculiar, something that immediately catches the eye. Its edges seem to wobble, to undulate ever so slightly. These subtle wobbles, these gentle undulations in the galactic fabric, were not mere quirks of the data. They whispered a profound ancient story to the scientists, a tale of cosmic violence and integration. They indicated with quiet certainty that our Milky Way had, in the distant past, crashed into another galaxy. Imagine two colossal cosmic ships moving in slow motion, their vast star-studded structures gently yet irrevocably merging into one. This was not a quick catastrophic explosion, but a prolonged, graceful, though no less impactful collision. Using the second grand data release, a dedicated team of researchers from the Netherlands, with painstaking care, sifted through the motions of 7 million stars. And there, amidst the predictable currents of galactic motion, they found something truly extraordinary. 30,000 stars were moving strangely. They were quite simply going the wrong way. While the vast majority of stars in our galaxy, including our own sun, move in a broadly coherent direction around the galactic center, this odd collection was defying the galactic flow, moving in the complete opposite direction. It was as if a small dissenting current had appeared in the middle of a vast river, moving against the prevailing flow. Their peculiar motion was not the only anomaly. Their color and brightness were also strangely distinct, setting them apart from the native inhabitants of our galaxy, like a patch of exotic wildflowers blooming unexpectedly in a familiar meadow. This unique celestial signature, combined with their retrograde motion, was a powerful indication that there was something truly special about this particular group of stars. The researchers, with their meticulous calculations, ran the numbers again and again, and what they found was astonishing. A model that perfectly fitted their observations was precisely what would happen if another galaxy had, in the deep past, collided with our own. This ancient collision, a cosmic event of staggering proportions, must have occurred an unimaginable 8 to 11 billion years ago. It involved a much smaller Hubble dwarf galaxy, which the researchers affectionately, and perhaps a little whimsically, named Gaia Enceladus, or sometimes with a touch of cosmic humor, the Gaia Enceladus sausage. Imagine this smaller galaxy like a compact star-filled cloud, gently inexorably plunging into the vastness of our nascent Milky Way. And as you visualize this, notice how its stars, indicated perhaps in a vibrant red in some cosmic illustration, actually managed to retain a fairly discrete sausage-like form. For a time, a coherent stream of alien stars, before eventually slowly gracefully spreading out across the colossal canvas of the Milky Way, becoming integrated into its very fabric. This ancient merger, this quiet act of cosmic consumption, may not have been just a dramatic event, but a fundamental part of how our Milky Way came to possess some of its unique characteristics. Could it be that this collision, this incorporation of another star system, was instrumental in the formation of the distinctive bar in the center of our galaxy? This central bar, a prominent feature in 2/3 of all spiral galaxies, is a mystery in itself. Gaia Enceladus might have been the catalyst, the spark that shaped the very heart of our galactic home. But the Milky Way, it seems, did not embark on a little late-night sausage eating just once. Our galaxy, it turns out, has a rather long and varied history of cosmic feasting. Another dwarf galaxy known by the enchanting name of Aruya Seoya Latoi was also found to have merged with the Milky Way, and perhaps with a touch of cosmic serendipity, Aruya Seoya Latoi might have even been a binary pairing with Gaia and Enceladus, two cosmic companions arriving together to be absorbed into our larger home. And then, in a later study, the whispers grew louder, revealing even more ancient meals. More than one additional dwarf galaxy's remnants were found scattered like crumbs after a feast. In fact, according to this particular study, our Milky Way, our seemingly peaceful home, may have consumed as many as 6 other galaxies throughout its long and eventful history. Each a small star-studded offering, slowly digested and integrated into the growing majesty of our own galaxy. And Gaia's data, ever vigilant, reveals that this cosmic feasting, this grand act of galactic consumption, has not stopped in the distant past. It is an ongoing process, a continuous slow-motion ballet of gravitational attraction. The nearby dwarf galaxy Sagittarius, a comparatively close cosmic neighbor, has already collided with our own Milky Way 3 times in the past 4 to 5 billion years. Imagine the gentle ripples, the subtle gravitational tugs each time these two celestial bodies pass through each other. And the dance is far from over. Sagittarius is set to collide with us again, a future event already written in the cosmic movements Gaia has so painstakingly observed. Perhaps in a thought that sends a shiver of wonder down the spine, this very collision, these ancient encounters with Sagittarius, may even have been the spark that lit the flame of our very own sun. Our sun came into being around that same turbulent time, a testament to the idea that cosmic chaos can be the ultimate creator. Eventually, in the deep, unimaginable future, Sagittarius itself may well become galaxy number 7, that the Milky Way has consumed all of its stars. Its cosmic dust, its very essence, being slowly ripped away, gently absorbed, and brought into the ever-expanding embrace of our own galaxy. It's a slow, beautiful, and utterly profound act of cosmic incorporation. These revelations, these quiet whispers from the cosmic deep, are but some of the incredible discoveries that have been made possible through the sheer volume and precision of the Gaia telescope's data. And it is for this profound reason, this unveiling of so many hidden truths, that it feels a touch sad, a little wistful, to acknowledge that Gaia's time, its grand mission of cosmic cartography, has indeed come to a close. Imagine a tireless artist having completed a masterpiece of unprecedented scale and detail, finally laying down their brush. There's a quiet ache in the knowing that the act of creation has ceased, even as the beauty of the work endures. For over a decade, Gaia maintained its delicate watchful position in the second Lagrange point, a stable gravitational sweet spot in space, like a patient sentinel. It did so using judiciously applied cold gas propellant, a mere dozen grams a day, a whisper of breath, keeping it perfectly aligned. But even the most carefully managed resources are finite, and that precious cold gas has at last run out. On the 15th of January, with its cosmic eyes still wide open, Gaia took its very last observation, capturing one final precious glimpse of our universe. Since then, it has begun the slow, graceful process of performing a few last calibrations, like a dancer stretching after a grand performance before finally powering down completely on the 27th of March, 2025, a quiet farewell to a truly extraordinary mission. But let us not linger too long on the quiet ending for Gaia's story. Its legacy of light and discovery is far from over. In fact, it continues to unfold, promising even more profound revelations from its collected wisdom. 2 more grand data packets, 2 more vast libraries of celestial secrets still await their release to the eager scientific community and curious minds around the world. The first of these, Data Release PR4 or DR4, is poised to be a monumental unveiling. It will encompass a staggering 500 terabytes of information, a digital universe in itself, and is slated for release in 2026. Think of it, 500 terabytes of cosmic data. Enough to stream a 4K video continuously for nearly 3 years straight, a river of light and knowledge. What makes DR4 particularly exciting is that while it will cover only the first 5.5 years of Gaia's mission, it will do so to an incredible, almost unimaginable level of detail. Imagine taking a snapshot, but then zooming in and zooming in further, revealing every minute ripple, every subtle nuance. This enhanced precision holds the promise of truly groundbreaking discoveries. Its exquisitely precise measurements of stars' minute wobbling motions, those tiny, almost imperceptible jiggles, might even highlight the possible locations of unseen exoplanets, distant worlds, subtly tugging at their parent stars. And beyond that, DR4 is set to create the largest catalog of binary stars to date, unveiling countless cosmic pairs, locked in gravitational dances perhaps for eternity. Each wobble, each pairing a new story written in the stars. It's also important to remember that the profound discoveries Gaia has brought us don't end with just prior or ongoing galaxy impacts, those grand cosmic feasts we've just contemplated. Its data offers us an even more exhilarating peek into the future and a deeper understanding of galactic mechanics. It's possible, with the sheer volume and precision of Gaia's observations, to fast forward the data, to run cosmic simulations, to model the motion of our local stars, millions of years into the future. Imagine a celestial time lapse accelerated to show the slow, majestic ballet of stars over eons. This allows us to see incredible models' animated dances of light that truly bring the universe to life. As you consider such a cosmic animation, notice how, although the stars near us initially seem to spread out across the Milky Way, gently drifting apart like leaves on a pond, they later reconvene, coming together again in a beautiful, ordered pattern. This regathering is thought to be due to what we call density waves. These aren't solid structures, but rather like slow-moving cosmic traffic jams, where stars and gas pile up, then disperse only to pile up again. Seeing this intricate cosmic play out, observing the subtle ebb and flow of stellar populations, helps to explain the very spiral arm shape of our galaxy. The arms aren't static, rigid structures, but rather beautiful dynamic patterns eternally forming and reforming as stars gently pass through them. Beyond the grand galactic scale, Gaia's data has also quietly yet powerfully helped improve our picture of events, much closer to our cosmic home right within our own solar system. Gaia, with its unwavering gaze, meticulously revealed the precise positions and directions of travel for over 150,000 asteroids in our solar system. Imagine a cosmic traffic controller suddenly gaining a clear, comprehensive view of every single rock and pebble orbiting our sun. This immense catalog alone is a monumental achievement, providing an unprecedented understanding of our neighborhood. But Gaia, ever the keen observer, went further. Thanks to its unparalleled ability to meticulously track those asteroid movements over extended periods, it was able to demonstrate something truly astonishing. 152 of these rocky wanderers probably have moons. Yes, little companions, tiny celestial dance partners orbiting their larger asteroid counterparts. This was revealed by the slightest wobbles, the most subtle gravitational tugs in these asteroids' trajectories. Think of it like watching a small child on a swing and noticing a tiny, almost imperceptible tremor in the swing's arc, hinting at an even smaller child, perhaps clinging to their back. This discovery nearly doubles the number of such binary system asteroids that we are aware of, opening up entirely new avenues for studying the formation and evolution of these rocky remnants of our solar system's birth. Gaia has rightly been called a treasure trove, and it is truly difficult to overstate just how much information, how many untold stories can be found embedded within its massive data releases. Imagine a vast untouched chest, overflowing with glittering jewels, each one a piece of cosmic wisdom. Gaia has provided us with the largest ever 3D map of quasars across the wider universe, identifying a breathtaking 1.3 million of these incredibly luminous objects. Some of these quasars, those furthest away, were spotted at the very edges of the observable universe, their ancient light having begun its journey when the universe itself was only a tender 1.5 billion years old. To gaze upon their light is to look back in time to witness the universe in its energetic, youthful prime. And right here in our own galactic neighborhood, Gaia has gently pulled back the veil to reveal a previously unknown black hole within our Milky Way. Not just any black hole, but one of truly massive proportions, weighing in at 33 times the mass of our Sun. And perhaps even more astonishingly, it's located a mere 2,000 light-years away from us, practically in our cosmic backyard. This particular type of black hole, this silent giant, had never been seen in our galaxy before. Most local black holes we knew of were only about 10 times the mass of the Sun, making this new find truly monumental. It's like discovering a hidden sleeping giant in a familiar forest, one far larger than any you'd expected to encounter so close to home. Many more such quiet, profound discoveries can be found waiting patiently to be unearthed, thanks to Gaia's meticulously collected data. It comes as no surprise, then, that ESA, the European Space Agency, is already quietly considering plans for a successor, a kind of cosmic heir to Gaia's grand legacy. This potential replacement, tentatively named Gaia NIR, standing for near infrared, would be a space telescope similar in spirit and purpose to Gaia, but with a crucial enhanced ability. It would be able to see much further into the infrared spectrum. This would allow it to pierce through those very same gas clouds, that cosmic fog that so often obscured Gaia's vision, opening up entirely new vistas of discovery. Imagine the clarity, the unfiltered view it would offer, but let us not hold our breath for this one, for the wheels of cosmic exploration turn slowly and deliberately. If it goes ahead, Gaia NIR is projected to launch in 2045, allowing for a substantial deliberate gap between that mission and Gaia's. This strategic pause is not a delay but a wise design. It would allow ESA to take even more advantage of the precious phenomenon of parallax. With such an extended intervening time, Gaia NIR would be able to observe how much further Gaia's observed stars have traveled in the intervening decades, providing an even more expansive baseline for incredibly precise distance measurements. It's a vision for the future built on the foundations of past wisdom, and when it finally comes out, there is one data release that is universally anticipated as the big one. Data Release 5, or DR5, is tentatively set to be released by the end of this current decade. This final colossal data release will include absolutely everything, all 10.5 years of Gaia's meticulous mission to the highest level of detail imaginable. It will truly be the ultimate treasure trove of information, a cosmic library beyond compare. Just think what new discoveries, what profound insights can be made with so much raw data to sift through, to ponder, to weave into new understandings of our universe. Who knows what else we will learn about our galaxy, what ancient stories or future pathways will be revealed. So while Gaia's mission coming to a close undeniably brings a touch of sadness, a quiet farewell to a tireless friend, the wealth of data it has collected is also incredibly wonderfully exciting. Our Milky Way galaxy, our beloved cosmic home, might indeed be surprisingly hard to learn about, its secrets veiled by its very embrace, but Gaia's data, its enduring legacy, will undoubtedly give us the best crack at it to date, pushing the boundaries of our understanding further than ever before. It's a promise of quiet revelations, of gentle awakenings to the deeper truths of our universe. We've all seen pictures of galaxies, haven't we? Often they are glorious objects, painted across the cosmic canvas with spectacular colors and shapes, swirling nebulae and blazing star clusters. However, Because they are often presented as static images frozen moments in time, one might quietly wonder, how do they truly rotate? What kind of cosmic dance unfolds within their vast, star-studded structures? The first obvious thought, perhaps a natural one, is that they spin around a central axis, much like a solid record on a turntable, looking something like this as they do so. But what if I were to whisper a secret to you, a gentle truth, that this intuitive thought is in fact totally wrong? For a start, galaxies are not solid objects, not rigid disks spinning uniformly. Instead, they are made up of millions to trillions of individual stars, each a sun, a star system, a world all floating in a vast, diffuse ocean of gas and dust. Imagine a colossal swarm of fireflies, each following its own unique path, yet collectively moving in a grand, coherent flow. While it's true that most of these individual stars are generally going in the same broad direction, circling the galactic core, their movements are not bound by the rigidity of a solid body. Each star, a tiny dancer, follows its own intricate orbit, a delicate gravitational ballet. But there is an even more profound reason, a cosmic subtlety why a spiral galaxy does not simply orbit like that initial intuitive example. If it were to spin as a solid disk, the fundamental principle of angular momentum would dictate that its graceful spiral arms would wind up tighter and tighter, like a spool of cosmic thread, until they became indistinguishable, utterly lost in a blurred uniform disk. Yet when we observe these magnificent cosmic pinwheels, we do not see this. Their arms remain distinct, flowing beautifully defined. So this tells us with quiet certainty that something else, something far more dynamic and elegant, must be at play. The leading theory, a beautiful and complex idea, suggests that these arms are not fixed structures, but are instead caused by density waves. Imagine a perpetual traffic jam on a cosmic highway where stars and gas slow down, bunch up, and then speed up as they pass through specific regions. These regions of higher density, these subtle compressions in the galactic flow, create the visual effect of spiral arms, meaning a galaxy's rotation would in fact look more like this, a swirling pattern, where the arms themselves largely stay in place, or at least move exceedingly slowly, as individual stars and gas clouds gracefully pass through them, like cars flowing through a recurring bottleneck. Within these cosmic traffic jams, these density waves is where the majority of star formation takes place in a spiral galaxy. The gas and dust, those fundamental building blocks of new suns, naturally clump up and are compressed in these denser regions. This is precisely why you so often see vibrant, glowing stellar nurseries, those beautiful nebulae dotting the spiral arms like precious jewels strung along a cosmic necklace. The arms themselves are also brighter, not just because there's a higher concentration of stars, but also because all the hot young bright stars, those blazing blue giants, are predominantly found in these very regions. These energetic, short-lived stars are born within the density waves, and by the time they might begin to drift away, many of them will have already burned out in spectacular fashion, returning their elements to the cosmic soup, leaving only the older, cooler stars behind. Another fascinating phenomenon intricately linked to spiral galaxies, and indeed to our understanding of the universe's grand design, is something subtly caused by the presence of dark matter. In the early universe, when dark matter was thought to be more diffuse, more evenly spread out like a fine mist, the stars within galaxies that were dominated by normal visible matter would have orbited much slower around the outside of the galaxy compared to those closer to the bustling center. Imagine a cosmic merry-go-round where the outer horses lagged considerably behind the inner ones. However, today, as we observe the vast, shimmering galaxies, we see something quite different. Stars are moving a lot faster, with a surprising uniformity even near the very edge of the galaxy. This unexpected speed, this additional gravitational embrace, is thanks to the powerful, yet invisible influence of dark matter. Dark matter, that profound cosmic mystery, cannot be seen or observed in any direct way. We know of its presence only through its gravitational influence, like an invisible hand, gently yet firmly guiding the cosmic dance. It seems that over the vast spans of cosmic time, dark matter has gently clumped, drawn together by its own gravity, coalescing towards the centers of galaxies. This concentration of unseen mass, this invisible core, causes stars to orbit faster than they should, if we were to account only for the gravity from the normal visible matter we can see. It is a constant reminder that the universe holds far more secrets than meet the eye, and that our understanding is ever evolving. Of course, other intriguing theories also exist to explain this phenomenon, alternative whispers in the cosmic wind. But these, if proven true, would require us to fundamentally change the very way we currently understand the laws of physics itself, a truly revolutionary thought. So, how do we even begin to grasp this subtle yet profound change in the way stars orbit galaxies over cosmic eons? The answer, like so many cosmic revelations, lies in the gentle art of looking back in time. When we gaze at extremely distant objects, at galaxies billions of light years away, their light has taken so long to reach us that we are, in essence, seeing them as they were in the ancient past, billions of years ago. And when we observe these distant youthful galaxies, the stars within them indeed seem to orbit slower than the stars in galaxies much closer to us, those we see as they are now. This subtle yet consistent effect scales beautifully with the distance to the galaxy, providing a profound observational window into the universe's evolving gravitational ballet. Of course, in the vast tapestry of the cosmos, there are always a few rule breakers, a few rebellious outliers that challenge our neatly formed theories. While most galaxies, those magnificent cosmic pinwheels, possess stars that orbit in this generally predictable manner, a few have been spotted that present a bewildering twist. They have leading outer arms. Imagine a spiral galaxy where the arms appear to be pulling the galaxy forward rather than trailing behind its rotation. One striking example is NGC 4622, a truly bizarre galaxy that rotates in the very direction its arms are pointing. This was understandably hard for astronomers to accept at first, a cosmic anomaly defying intuition. But the universe, in its intricate complexity, often offers solutions to its own puzzles. Eventually, smaller inner arms were also discovered in NGC 4622, providing a crucial clue. This unusual galactic configuration, this apparent defiance of the cosmic norm, has probably experienced a merger in its not-too-distant past. A dance with another galaxy, a gravitational tug-of-war, likely caused this peculiar phenomenon, twisting its arms into an unexpected leading position. It's a testament to the transformative power of cosmic encounters. Another such captivating rule-breaker is the enchanting Black Eye Galaxy. This particular cosmic marvel exhibits a truly remarkable feature: two counter-rotating disks of gas and dust. Imagine two colossal cosmic turntables, one spinning clockwise, the other counterclockwise, nested within the same galactic structure. The inner disk, where you can clearly see all the dark, intricate dust lanes, rotates normally, flowing with the general galactic current. However, the gas in the outer disk rotates in the completely opposite direction, a graceful yet defiant counter-movement. Interestingly, the stars in this outer region do not seem to be orbiting retrograde. It is primarily the gas that performs this elegant backward dance. This observation offers intriguing possibilities. It is believed that this unusual behavior might be due to gas still being fed into the galaxy from the vast intergalactic medium, a continuous slow infusion of new material. Or perhaps this galaxy, too, experienced a past merger with another galaxy, one that was exceptionally rich in gas, introducing a new counter-rotating component to its already complex structure. Each anomaly, a new door to understanding the universe's boundless creativity. Now let us turn our attention to the other major category of galaxy, a type that at first glance might seem to lack the dramatic flair of its spiraling cousins, yet holds a profound story of cosmic maturity and quiet transformation. These are the elliptical galaxies. Imagine, if you will, a grand ancient city, its bustling construction days, long past its vibrant youthful energy, now settled into a serene, almost timeless tranquility. Unlike the dynamic swirling spirals, elliptical galaxies contain stars that are generally much older, like a population of wise, seasoned elders. The reason for this venerable age lies in their very nature. The dust lanes, those swirling nurseries of gas and dust that feed the birth of new stars and spiral galaxies, have largely been exhausted in ellipticals. They have been used up, converted into the luminous points of countless stars over eons of cosmic evolution. This means that stellar production has all but stopped a quiet cessation of new life. It's as if the cosmic quarries have run dry and no new bricks are being laid for new stellar buildings. What remains is a galaxy of enduring, long-lived stars, each following its own rather elliptical orbit, largely independent of its neighbors. A gentle, almost solitary dance in the vastness, sometimes in the wondrous tapestry of the cosmos. Galaxies can exhibit characteristics of both types, a beautiful blending of youth and age, of dynamic change and quiet maturity. These fascinating transitional forms are known as lenticular galaxies. Imagine a city that once hummed with the energy of construction, but whose building materials are now dwindling. These galaxies often possess remnant dust rings, like faint ghostly halos which haven't been fully exhausted yet. Their overall appearance, stripped of the vibrant star-forming arms, can be quite ghostly, a testament to their transitional state. The very act of star formation, that constant replenishment of young hot stars, appears to be a crucial factor in keeping spiral arms defined and vibrant. Once those stellar building blocks, the gas and dust, begin to dry up, we've observed countless examples of spiral galaxies gently losing their sharp definition, their graceful arms blurring into a softer, less distinct form. Perhaps then, lenticular galaxies are truly the midway point, the poignant bridge between the active star-forming spiral galaxies and the serene, quiescent elliptical galaxies. They are caught in a moment of cosmic reflection, having lost their youthful vigor, but not yet fully settled into the ancient calm of old age. So there we have it, a quiet look at how galaxies, these colossal cities of stars, rotate and evolve. The universe, in its boundless expanse, is truly full of secrets, infinite layers of mystery waiting to be unveiled. And some of the most incredible ones are hiding just beyond the reach of our everyday vision, beyond the spectrum of visible light, cloaked in cosmic dust. What if I were to whisper to you that more than 1.5 billion unseen objects from distant nascent galaxies, struggling to be born to vibrant newborn stars, still swaddled in their gaseous cocoons, and even some of the very oldest stars in our entire Milky Way, are sitting just out of our conventional reach, patiently waiting to be found? That's a little frustrating to ponder, isn't it? To know that so much beauty, so much knowledge lies just beyond the visible veil. Until now, that is, because thanks to the tireless efforts of the European Southern Observatory and its magnificent Visible and Infrared Survey Telescope for Astronomy, or VISTA, we can at last begin to gently lift that veil on these hidden wonders. Imagine being given a pair of magical spectacles that allow you to see through walls, revealing the bustling life within. VISTA is our cosmic version of such a gift. For the first time in human history, we now possess a truly comprehensive infrared map of the Milky Way. A map that, like a wise elder sharing ancient secrets, pierces through the obscuring fog of space. It reveals an unprecedented view of our galaxy, a more intimate portrait of its intricate structure, and even offers tantalizing glimpses of what lies beyond its familiar boundaries. It's a profound moment in our journey of cosmic understanding. In a landmark achievement in September 2024, VISTA published the largest and most detailed infrared survey of the Milky Way ever undertaken. This monumental undertaking wasn't a quick glance, but a patient, persistent gaze encompassing a 13-year period from 2010 to 2023. Over 140 nights of tireless observation, Vista meticulously captured around 200,000 images each, a pixelated whisper from the cosmos. This resulted in the generation of a staggering 500 terabytes of data. Pause for a moment and truly consider that volume, 500 terabytes. That's the same immense amount of data as it would take to stream a 4K video for nearly 3 years straight without a single pause. A river of pure, unfiltered cosmic information. Vista itself is an integral part of ESO's Paranal Observatory, nestled high in the arid, clear skies of Chile. Its primary focus, its guiding purpose, has always been to map large areas of the sky, to capture vast swaths of the cosmic tapestry with unparalleled detail. And at the heart of this endeavor lies Vista's infrared camera, affectionately known as VirCam. It was with this sophisticated instrument that the dedicated team of astronomers was able to truly peer through the dense dust and gas that permeates our galaxy like an invisible mist, and finally begin to uncover some of the Milky Way's most hidden, most mysterious places. Traditional telescopes, the workhorses of astronomy for centuries, allow us to view the cosmos in visible wavelengths, the light our human eyes are accustomed to seeing, ranging between about 380 to 700 nanometers. This is the vibrant rainbow of colors we perceive from deep violet to fiery red. But Vista, in its wisdom, isn't constrained by these familiar boundaries. Instead, it operates at infrared wavelengths, specifically between 900 and 1/200 nanometers. This subtle yet profound shift in perception is akin to gaining a new sense, an ability to detect an entirely different kind of light. This unique capability allows Vista to detect otherwise invisible objects, those that simply vanish in conventional visible light. Imagine countless stars perhaps shrouded by thick veils of dust, their light unable to break through to our visible light telescopes. Vista pierces these veils, revealing the gentle glow of these hidden suns. It also excels at finding cold brown dwarfs, often referred to as failed stars. These enigmatic objects, too massive to be planets, yet too small to ignite true nuclear fusion and become stars, don't emit enough visible light to be seen with a traditional telescope. But in the infrared, their faint residual warmth glows, making them detectable to Vista's sensitive gaze. It's like finding warm embers hidden in the cool ashes. To truly grasp the transformative difference between visible and infrared light, imagine these two views of a familiar cosmic beauty. The Lobster Nebula, also known as NGC 6357. One image captured in visible light presents a breathtaking scene, but perhaps with certain areas obscured, swallowed by dense, dark clouds of dust. Now contrast this with a second image taken with Vista's infrared camera. What do you see? Suddenly, miraculously, the dust that once obscured our field of view seems to vanish to become translucent, revealing what looks like hundreds of thousands, or perhaps even millions, of previously invisible stars. It's like pulling back a heavy velvet curtain to reveal a glittering hidden world, vibrant with life that was always there, just waiting to be seen. This groundbreaking map, this profound new understanding of our galactic home, was meticulously created through the combined efforts of two companion projects, the Vista Variables in the Via Láctea VVV survey, and its companion, the VVV Extended Survey, VVX. Via Láctea, of course, is the beautiful Latin name for the Milky Way, a poetic nod to the cosmic river of light. The sheer volume and quality of the data collected from these two tireless companion projects, which collectively form the Vista Infrared Survey, have already led to an astonishing wealth of knowledge, with over 300 scientific articles already published. Each paper, a quiet revelation, adding another brushstroke to our unfolding understanding. Unlike some other recent space maps, which might focus on specific regions or types of objects, this particular infrared survey stands out as one of the most detailed and comprehensive ever made. Its scope is truly immense. It is the very first infrared survey to cover nearly 80% of the Milky Way's luminous mass, encompassing the vast majority of our galaxy's star-filled expanse. And perhaps even more critically, it provides the largest infrared catalog ever made of our galaxy's central region, that dense, bustling heart that has remained so stubbornly obscured. This unprecedented detail allows astronomers to study our galaxy in finer detail than ever before, to truly zoom in on the intricate structures and the quiet movements within. This survey, this gift of light, gives us an accurate 3D view of the inner regions of the Milky Way, those mysterious realms that were previously hidden by the persistent curtain of cosmic dust. It covers an area of the sky equivalent to a staggering 8,600 full moons, a canvas of immense proportions. And within this vast cosmic tapestry, it contains about 10 times more objects than any previously published infrared map from 2012, marking a quantum leap in our observational capabilities. Our Milky Way, as we understand it now, consists of a prominent central bulge, a dense, bright, slightly puffed-up collection of ancient stars with a flat disk of 2, perhaps 4 elegant spiral arms gently wrapping from its ends. This image, this visual representation, shows us the precise area of our galaxy that was so meticulously mapped in the VISTA survey. The red squares, vibrant markers against the cosmic backdrop, denote the central regions of the galaxy. These were the areas observed by the original VVV survey, and then patiently reobserved with even greater detail by the extended VVX survey. The other square colors stretching outward show areas that were observed only as part of the extended survey, broadening the reach of VISTA's infrared gaze. From this intricate map, you can clearly see that these surveys have focused their keen infrared eyes right on the central plane of our galaxy, spanning a significant part of the disk, and most of that mysterious nuclear bulge diving deep into the galactic core. But what then has VISTA, this tireless cosmic explorer, truly revealed? The words of Argentinian astrophysicist Dante Maniti, who so passionately led the survey project, echo with a quiet triumph. We've made so many discoveries. We have changed the view of our galaxy forever. And as much as one would love to linger on every single one of these profound revelations, to unravel every thread of this cosmic tapestry, it's probably best we gently stick to some of the brightest highlights, the most radiant pearls from this treasure trove. As part of the survey in the year 2015, VISTA turned its patient attention to the star formation region of Messier 20, more lovingly known as the Trifid Nebula. This breathtaking cosmic cloud, a nursery for new suns, lies approximately 9,000 light-years from Earth, a relatively close neighbor in the grand scheme of the galaxy. When viewed in visible light, as in this familiar image, we see a truly beautiful nebula glowing with a soft, ethereal pink from the emission of ionized hydrogen gas, surrounded by a delicate blue haze of scattered light from young hot stars. The dense clouds of gas and dust within it seem to obscure the star-filled space behind, like a beautiful painted curtain drawn across a cosmic stage. Now gently shift your gaze to this second image, the one taken by VISTA's infrared camera. What a profound transformation! Peering beyond the very clouds that once formed the curtain, VISTA's infrared eye reveals a whole swarm of new stars glittering like scattered diamonds, previously hidden from our sight. This image, in its luminous clarity, not only allows us to see right through the Trifid Nebula itself, but by a stroke of beautiful cosmic chance, it revealed objects on the far side of our galaxy that had never ever been seen before. It was a true unveiling, a sudden glimpse into the cosmic beyond. To their profound surprise and quiet delight, astronomers identified 2 faint red objects among this newfound multitude as Cepheid variable stars. Remember those reliable cosmic yardsticks we spoke of earlier? While they appeared in the image to be nestled just behind the visible edge of the Trifid Nebula, their true cosmic address told a far more astonishing story. In reality, they are incredibly distant, approximately 7 times farther than the nebula that had so effectively helped to block them from our view in visible light. Imagine a tiny light seemingly just behind a nearby mist, but in truth, twinkling from miles beyond. Cepheid variables are a truly unique type of bright star inherently unstable, their luminosity waxing and waning with a beautiful, predictable rhythm. They brighten and fade over a period of a few days or a few months, depending on their intrinsic brightness. The very first variable star we ever identified in modern times was Omicron Ceti, affectionately known as Mira. It had been described as a nova, a new star suddenly appearing until the year 1638, when the diligent astronomer Johannes Hevelius observed it repeatedly getting brighter and dimmer in a precise cycle that lasted approximately 11 months. It was a cosmic clock ticking its own unique time. As for this particular pair of newly discovered stars, these distant Cepheids revealed by VISTA, they are remarkably the only ones we have identified so far in this specific location. This location deep beyond the central bulge on the far side of our galaxy was previously a complete mystery, a blank spot on our cosmic map. And this is precisely why they are so incredibly useful. You can indeed think of them as a kind of cosmic yardstick, a reliable measure that can be applied to distances stretching tens of millions of light years. They are the fixed points, the known quantities in a universe of vast unknowns. If you know how long a star's pulsation period is, that precise rhythm from bright to dim, then you can infer its absolute brightness, its true luminosity, as well as its approximate age. And once you have that absolute brightness, you can compare it to the apparent brightness, that is, the amount of light that actually reaches our telescopes here on Earth. This simple comparison, this elegant ratio, provides a direct measure of how distant the star truly is. With just a few reference points like these scattered cosmic lighthouses, we can begin to build up a real three-dimensional picture of the immense scale of our galaxy, and even venture beyond its familiar boundaries into the wider universe. It's like finding a few familiar landmarks in a vast uncharted territory, allowing us to slowly, patiently map the entire landscape. Looking toward the galactic center, that bustling veiled heart of our Milky Way, a dedicated team of astronomers and data scientists, guided by the luminous whispers from VISTA, found an even greater bounty more candidate Cepheid stars, a remarkable 655 in fact. Imagine a quiet, persistent search through a vast cosmic garden unexpectedly yielding a multitude of rare pulsating blossoms. They then meticulously sorted these newfound celestial pulses into one of two classes, a careful categorization of their unique rhythms, and in their patient work, they uncovered a truly exciting truth. 35 of these 655 stars were classical Cepheids, the younger, more vibrant, and astronomically useful of the two types. This was a discovery that resonated with quiet excitement throughout the scientific community, especially since the galactic bulge, that ancient central hub, was long thought to contain mostly elderly stars, a population at least 8 billion years old, like a venerable assembly of cosmic elders. The prevailing wisdom suggested that this region was a place where star formation had long since ceased, leaving behind a quiet, settled population. But VISTA, with its infrared eyes, whispered a different story. Recording their precise pulsation periods, the team revealed that all 35 of these young Cepheids were less than 100 million years old, a mere blink of an eye in cosmic terms. And some of them, even more astonishingly, may be as young as 25 million years old. To put that in context, our own sun, our familiar source of warmth and light, is approximately 4.5 billion years old. So the youngest Cepheid discovered has only been around for a fleeting 0.6% of our sun's long, majestic lifespan. It was a clear, undeniable sign of ongoing recent star formation in a place thought to be ancient and quiet. The team's exploration of these vibrant young Cepheids culminated in yet another major discovery, one that reshaped our understanding of the very structure of our galaxy. By meticulously mapping the precise locations of these 35 classical Cepheids, they had found the team was able to trace a completely new feature in the Milky Way, a thin disk of young stars that stretches right across the galactic bulge, buried deep behind those thick, obscuring clouds of gas and dust. It was a hidden pathway, a secret stream of youth that had remained utterly unknown in all previous surveys of the region. Imagine finding a vibrant hidden river flowing through the heart of an ancient mountain, its presence unsuspected until now. In revealing this delicate yet profound structure combined with the discovery of all these young Cepheids, scientists have been able to infer that there has been a continuous stream of star formation along the midplane of the galaxy for the past 100 million years. This wasn't a sudden burst, but a steady, ongoing cosmic engine humming softly in the galactic core. And tantalizingly, there might be even younger Cepheids out there still hidden, still waiting to be discovered. These potential cosmic infants would be so incredibly bright that their light would simply saturate or overwhelm the sensitive detectors of the VVV survey, like a blinding flash, making it impossible to see the delicate details. They are simply too luminous for our current tools to properly observe a beautiful irony of the cosmos. The fact that we found this thin disk of young stars, these fresh faces within the very heart of the galactic bulge, is nothing short of incredible. We used to think that the galactic bulge was an ancient, perhaps unchanging feature of our galaxy's distant past, a place where exclusively old stars had formed separately from the dynamic stellar disk. It was perceived as a relic, a fossil of the early universe. But this groundbreaking finding gently yet firmly reveals that things aren't so black and white, that the cosmos is far more nuanced than we often assume. It whispers that the formation of newer stars within the bulge could be a natural continuous progression of our galaxy's grand evolution, a persistent pulse of life even in its most ancient core. But even more inspiring, perhaps, is a discovery brought forth by the VISTA infrared survey that lies at the very ancient heart of our Milky Way galaxy. In 2016, for the first time in human history, a particular type of ancient star known as an RR Lyrae variable star was discovered right in the bustling center of the Milky Way galaxy. This profound discovery was made by a dedicated team led by the astrophysicist Dante Maniti, the same gentle guide of the VVV survey, and Rodrigo Andreas Ramos. These RR Lyrae stars are like cosmic archaeological finds. This type of star is usually found far away, typically in globular clusters, which tend to orbit the outer, more serene regions of the galaxy. A globular cluster, you see, is a tightly packed, almost spherical group of stars, a cosmic city containing tens of thousands to millions of stars, all bound together by the invisible threads of gravity. And what makes them so special is their antiquity. They are truly ancient, harboring a stellar population that can be over 10 billion years old. These are the firstborns, the venerable pioneers of the galaxy. The team found 12 RR Lyrae stars during the VVV survey's patient gaze into the galactic center. Their presence, so unexpected in this youthful region, suggests that they might be the scattered remnants of an ancient globular cluster, a venerable cosmic ancestor that once resided right at the very heart of our galaxy, perhaps broken apart and dispersed by the immense gravitational forces there. This subtle clue from the stars provides compelling evidence that might help astronomers decide between two competing grand theories of how nuclear bulges, those central hubs of galaxies, actually form. While some scientists theorize that the nuclear bulge forms incredibly early in the galaxy's evolution, a dramatic birth, where multiple smaller galaxies violently collide and merge, creating a chaotic maelstrom of stars and gas, others suggest a more gradual organic growth. This second theory posits that the bulge forms slowly over time, where gas is continuously funneled inwards, gently triggering waves of star formation, building the bulge layer by layer. Finding these ancient stars, these venerable RR Lyrae, right here in the galactic center, lends strong support to the first theory. Their presence whispers of a tumultuous past, a dramatic beginning. It suggests that the bulging heart of the Milky Way likely grew through the forceful, yet ultimately formative merging of primordial globular clusters, those ancient star-filled spheres, like cosmic building blocks, assembling to form a grander structure. Therefore, it supports the idea of a violent, chaotic, yet ultimately creative birth for the galactic bulge. So this discovery not only hints at the dramatic beginnings of our own galaxy, but it also offers compelling evidence into how these magnificent galactic bulges might form in other similar galaxies across the vast universe. It's a key to understanding the deep cosmic past. Speaking of ancient stars, VISTA, in its diligent infrared survey, was also able to unearth another 2 new globular clusters themselves, adding to our growing catalog of these venerable star cities. Imagine finding lost cities of antiquity hidden from plain sight. In this visible light image, a previously known globular cluster, UKS-1, can be seen on the right, appearing as a hazy, reddish splotch, a dim, distant whisper of stars. This cluster had until these new discoveries held the distinction of being the dimmest known globular cluster, a quiet, almost forgotten corner of the galaxy. Now gently compare this same patch of sky, but this time bathed in VISTA's penetrating infrared light. Suddenly, magically we can see what we have been missing. Much more faint than the already dim UKS-1, we can now clearly make out a second globular cluster twinkling faintly in the upper left of the image. This newly unveiled cluster has been aptly named VVV-CLAUMDUL1, a simple designation for a profound discovery. And not long after another equally elusive globular cluster was found aptly named VVVV-CLONROBCE2. This small faint group of stars may hold another record. It could be the closest known globular cluster to the very center of the Milky Way, a hidden gem nestled near the galactic heart. Did you know that before these new discoveries by VISTA, there were only 158 known globular clusters in the entire Milky Way? To have the VISTA survey in its relatively short lifespan identify 2 more of these rare ancient stellar objects is truly quite a significant accomplishment. It's like finding 2 more incredibly rare ancient artifacts in a seemingly well-explored archaeological site. Within this bustling central region of the galaxy, it is incredibly easy for younger, brighter stars and the omnipresent cosmic dust to completely obscure these faint ancient globular clusters, especially since their great age prevents them from shining as brightly as their youthful counterparts. But now that they've been revealed, these features bring exciting possibilities for further study, opening new avenues for understanding our galaxy's distant past. It could just be an illusion of perspective, a trick of cosmic alignment, but scientists in their endless curiosity have wondered whether VVV-CLAUMDUL1 is somehow gravitationally bound to UKS-1. If this were indeed the case, if these 2 ancient star cities were locked in a perpetual cosmic dance, then they would represent the Milky Way's very first known binary globular cluster pair. We have found such binary clusters in other galaxies, like those in Centaurus A and the Large Magellanic Cloud, hints that such pairings exist across the universe. But finding one right here in our own galactic backyard would be truly extraordinary. Scientists theorize that it might be when these gravitationally bound clusters, these ancient pairs, finally collide that we witness the birth of the most massive globular clusters, like the colossal Omega Centauri. So the quiet study of a potential binary cluster right here in our own galaxy could yield some truly amazing insights into this profound cosmic process, offering a window into the formation of the largest and most ancient star systems. It's all speculation at the moment, a gentle hypothesis whispered among the stars. But it's undoubtedly a cool and exhilarating thought, a glimpse into the dynamic, evolving nature of cosmic structures. In addition to these venerable globular clusters, the VISTA infrared survey, with its tireless gaze, identified a multitude of other types of star clusters, younger and more abundant. At least 96 new open or galactic clusters have been found. These typically contain fewer younger stars born more recently and are far more common than the ancient globular type. Like their older cousins, they had been hidden from our conventional sight by those ubiquitous veils of cosmic dust. But VISTA's 4.1-meter infrared telescope, with its penetrating vision, has gently lifted the curtain, revealing them in all their glory, allowing us to see countless new stellar nurseries and vibrant young stellar families. Take a moment to consider just a few of these stunning images. We now possess these breathtaking portraits of newly unveiled cosmic families. One of these open clusters, named VVVC-Z-3, is much more difficult to make out in images compared to the tightly packed globular clusters. Imagine trying to spot a loose collection of brightly lit houses amidst a sprawling, unlit countryside. Try to see the subtle density differences in the stars in this section of the image compared to the more diffuse surrounding regions. It's a delicate dance of light and shadow, a testament to its more spread-out nature. This particular cluster was found by VISTA, a staggering 15,000 light-years beyond the Milky Way's center, a true whisper from the galactic frontier. And in a remarkable twist, it also happens to be the very first of its kind to be discovered on the far side of the galaxy, a pioneering glimpse into previously hidden depths. The sheer scale of this survey, this monumental undertaking, is truly staggering, covering a vast, immense region of the sky and meticulously mapping more than 1.5 billion objects. This ocean of data has already led to fascinating discoveries, quietly rewriting our understanding of the Milky Way and even sending ripples of insight into the wider universe. And what we've discussed, what we've gently touched upon, is truly just the tip of the iceberg, a handful of shimmering jewels from a vast, untapped treasure chest. This survey will serve as a foundational map, a cosmic Rosetta Stone for future telescopes and observations. It will be the bedrock upon which new missions will build, hoping to expand on VISTA's incredible legacy with even higher resolution and greater sensitivity. We now possess the most detailed 3D map that has ever been made of the Milky Way's intricate structure and its myriad objects, a map that has unveiled hidden wonders previously beyond our reach. And scientists are already, with quiet determination, uncovering new galactic features, reshaping our understanding of the galaxy with every passing day. With the profound information gleaned from this groundbreaking infrared survey, combined with the recent equally remarkable work from ESA's Gaia mission, peering into the universe in visible light, it is truly an exciting time to be an astronomer, a time of unprecedented discovery. And we can expect a flurry of new insights, a cascade of understanding about our own galaxy and the universe as a whole in the years to come. VISTA's infrared observations have, with their gentle yet powerful gaze, unveiled dozens of hidden star clusters and millions of previously unseen stars. They have revealed new stellar nurseries, those bustling cosmic cradles where stars are born, and they have profoundly broadened our understanding of the very formation and evolution of our magnificent Milky Way. Looking at the sky through these different wavelengths with these new sets of cosmic eyes has truly ushered in a new era of galactic exploration, and one can only wait with bated breath, with quiet anticipation, to see what else astronomers and data scientists are going to uncover thanks to VISTA's detailed 3D map. Have a look at this beautiful image captured by the James Webb Space Telescope, a true marvel of our age. Immediately, your eyes are drawn to two distinct types of objects, each telling its own quiet story of cosmic distance and grandeur. First, you'll notice the nearby stars within our own familiar Milky Way galaxy. They appear as brilliant points of light, often adorned with shimmering diffraction spikes, like tiny perfect jewels scattered across a velvet cloth. These are our neighbors, our celestial companions. But further in the background, almost like ghosts of light, you'll see entirely new galaxies, each one a universe unto itself, containing billions of stars. These appear smeared out into soft elliptical blurs or graceful spiraling forms, distant islands of light in the cosmic ocean. What you probably won't see, however, are distinct individual objects within those other galaxies. They are simply too distant, their light blending together into a collective shimmer. Far too faint and diffuse to resolve individual stars from such unfathomable distances. But there is one remarkable exception to that rule, one type of object so incredibly bright that you can discern its solitary brilliance from billions of light years away. So luminous, in fact, that it stands out from all the surrounding stars in its entire galaxy, blazing like a cosmic beacon. This extraordinary object, my curious friend, is a quasar. But what if I were to whisper a truly astonishing secret to you? What if I told you that a whole bunch of tiny quasars were in fact hiding in plain sight, right within our very own Milky Way? How can this possibly be when quasars are by their very definition some of the brightest objects in the entire universe, outshining their host galaxies? In this quiet contemplation, we will gently explore how such a paradox is possible. We'll learn how a dedicated team of scientists used images of just one nearby microquasar, a smaller, quieter cousin, to gain a deeper, more profound perspective into the inner workings of quasars all over the universe. It is a story of unexpected light and of the grand interconnectedness of cosmic phenomena. I invite you to join me on this quiet journey as we unravel the story of these astronomical lighthouses, one cosmic photon at a time. It's a tale that begins not with light, but with an unfamiliar hum. Astronomers have patiently pointed their telescopes upwards at the night sky for centuries, using the familiar wavelengths of visible light to map the constellations and chart the planets. Yet it was only in the 1950s that they embarked on a groundbreaking quest to map out what the universe around us looks like, not in the comforting glow of visible light, but in the unseen waves of radio energy. Think of this as the astronomer's version of putting on night vision goggles, stepping into a new realm of perception. At first, they didn't see anything overtly out of the ordinary. Many of the same grand galaxies that emitted visible light also hummed with radio waves, so they could be seen with or without these new goggles, a comforting continuity in the cosmic tapestry. But then, amidst the familiar stars and galaxies that were already known to populate the night sky, astronomers began to glimpse something entirely new, something unexpected. They saw objects that shone with astonishing brilliance in radio waves, yet had never before been seen, or were barely perceptible in visible light. It was as if a hidden symphony had suddenly begun to play previously unheard, and it wasn't just one of these mysterious objects. By 1960, observations quickly grew, snowballing into hundreds of these enigmatic radio sources recorded across our sky. At the time, astronomers with all their vast knowledge didn't have the faintest clue what the origin of these powerful radio waves could possibly be. For all they knew in those early days of cosmic detection, these strange, powerful waves could have been emanating from a giant, complex intergalactic network of alien radios sending signals across the vast cosmic void. It was a thought both thrilling and deeply perplexing. But what they did learn from meticulous follow-up observations, using more precise and powerful instruments like the Hale telescope, was that you could indeed see these objects in the visible part of the spectrum. They were just exquisitely small and incredibly faint, mere pinpricks of light compared to the grand sprawling galaxies. They appeared as points like individual stars, not smeared out blobs or extended structures like galaxies. Yet they also couldn't be regular stars. For ordinary stars don't typically emit much energy at all in the form of radio waves, certainly not with this kind of staggering power. For this bewildering paradox, appearing like a star but emitting like something far grander and stranger, these mysterious objects came to be known as quasi-stellar radio sources. This name quite literally translates to something like a star but not quite a star, which emits a lot of radio waves. That rather cumbersome name eventually got shortened to something a little more palatable, a little more memorable, and indeed a little more enigmatic: quasars. Even with such a catchy and intriguing name, It took astronomers and physicists nearly 30 long years to truly pin down what these enigmatic quasars fundamentally were. And alas for those who dreamed of alien radios, the real answer, while still profoundly fascinating, was likely not that. It turns out that the explanation, like so many of the universe's grandest phenomena, centers around black holes. And not just any ordinary black holes, those silent cosmic devourers, but supermassive black holes, cosmic behemoths that can be millions or even billions of times the mass of our humble sun. These colossal gravitational wells are frequently found like silent, powerful hearts at the very center of large galaxies. And here's the cosmic magic. Although black holes by their very nature cannot emit any light themselves, their gravity is so powerful that even light cannot escape their embrace. They can paradoxically create quite the spectacle out of the material orbiting around them. This material forms what is known as an accretion disk, a swirling superheated whirlpool of gas and dust, spiraling ever closer to the black hole's event horizon. If you wish to dive deeper into the intricate details of quasars, you can always seek out older, more detailed explanations. But for now, allow me to offer a quick, gentle summary. Imagine matter, perhaps gas or dust, orbiting a black hole like water swirling down a drain. As this matter spirals inward, it loses energy due to immense internal friction, much like rubbing your hands together creates heat, and a vast portion of that lost energy, that incredible friction, ultimately gets converted into light streaming outward from the black hole with astonishing power. But in some cases, the accretion disk doesn't just emit light, it also powerfully spits out relativistic jets of ionized matter. These are like colossal cosmic fire hoses, powerful streams of particles collimated by incredibly powerful magnetic fields, aligned with the spin of the black hole and its immediate surroundings. The particles within these jets can propagate through the universe, traveling across vast intergalactic distances as cosmic rays, sending out radio signals as they are pushed around by the faint, ubiquitous intergalactic magnetic fields. Overall, quasars emit so much energy, such a torrent of light and radiation, that a single quasar in a distant galaxy will utterly outshine, completely overwhelm, the collective glow of the other hundreds of billions of stars in that galaxy combined. Think of a single blinding spotlight outshining an entire city at night. That's why, when quasars were first observed, they appeared as small as individual stars, mere points of light, but were far, far brighter than any single star outside of our Milky Way could ever possibly have been. Their sheer luminosity was their calling card across the cosmic void. Now our own beloved Milky Way has its very own supermassive black hole right there at its bustling center. We affectionately call it Sagittarius A Sharum. But for better or for worse, the accretion disk swirling around our black hole is at present too thin, too faint, too quiet to ever be called anything close to a quasar. It's like a gentle eddy in a calm stream rather than a roaring waterfall. And until something truly dramatic happens, perhaps a grand cosmic encounter like the predicted collision with the Andromeda Galaxy, scheduled for a few billion years in the distant future, Sagittarius A will likely remain calm and mellow, a sleeping giant at the heart of our home. On one hand, we are in a quiet sense quite lucky. A quasar blazing so close to Earth, so powerful and energetic, would emit enough high-energy radiation to be potentially fatal to terrestrial life, perhaps stripping away our atmosphere or bathing us in deadly rays. This thought naturally leads one to wonder about the kinds of life, the forms of existence that could possibly arise in galaxies that do contain these vibrant active quasars where the sky is illuminated by a second blazing sun. But on the other hand, a part of us, the deeply curious part, might feel a touch of longing. We're missing out on a second source of light in our night sky, illuminating our planet almost as brightly as the sun itself, a truly breathtaking spectacle. And oh, how incredibly cool it would be to get to study a quasar from up close, to directly observe its majestic power and intricate workings. So can you imagine my surprise and perhaps a touch of quiet awe when I learned that we might actually have the best of both worlds. Quasars alive and active right here in the Milky Way, and yet not so overwhelmingly powerful as to wipe out our entire biosphere. How, you might quietly ask, could this be possible? If the one supermassive black hole at the very center of our galaxy isn't a quasar, then where across the vast cosmic expanse of our home could they possibly be hiding? It took a couple of decades of patient observation and brilliant deduction, but scientists eventually made a profound discovery. Quasars can, in fact, form around ordinary black holes too, not just those colossal supermassive ones. These ordinary black holes, the remnants of collapsed giant stars, are far more common, typically only a few times more massive than our Sun. They are scattered throughout practically any galaxy, like invisible seeds sown across the stellar fields. You probably wouldn't expect one of these more modest black holes to have its own roaring accretion disk generating such immense light. But once in a while, a nearby orbiting star might wander too close, getting caught in its irresistible gravitational pull. This unfortunate star then acts as a steady source of material feeding the smaller, less deadly, yet equally fascinating version of a quasar, a microquasar. Even though the jets of a microquasar are much weaker than their full-scale galaxy-shining counterparts, they offer a unique advantage. Their proximity to Earth makes them far easier to study. Imagine trying to understand a distant roaring waterfall from miles away compared to observing a smaller, more accessible cascade nearby. This closeness allows us to learn far more intricate details about the properties and dynamics of both microquasars and, by extension, their larger full-scale counterparts that blaze across the intergalactic void. They are cosmic laboratories right in our own backyard. The very first microquasar, a quiet revelation, was discovered in 1979 and was given the rather straightforward name SS433. It was originally documented as the 403rd entry in a catalog of peculiar stars compiled by astronomers Nicholas Sanderleek and Bruce Stevenson just 2 years prior. To date, only a handful of microquasars have ever been found rare jewels in the cosmic crown. And SS433 in particular, perhaps because it was the first, has been a subject of widespread wonder and intensive research. Despite its unassuming name, SS433 is far more than just some ordinary star in a catalog. It is, in fact, a type of supergiant star orbiting around a stellar mass black hole locked in a perpetual dramatic dance within a binary system. As the black hole in this cosmic duo relentlessly accretes material, pulling gas and dust from its supergiant companion, it produces a powerful pair of jets. These jets are elegantly perpendicular to our line of sight from Earth, meaning that the jets themselves, those powerful streams of particles, will never actually hit us or reach our detectors directly. But as these jets propagate outward, streaming into the vastness of space, they emit light in all sorts of directions, scattering their luminous whispers throughout the cosmos. This allows us to image them across various wavelengths, from radio to X-ray to gamma ray, and to learn more about how they are produced. How these incredible cosmic engines truly work. One of the first intriguing things we observed about SS433 was that it actually produces two distinct types of jets, like a nested set of cosmic fountains. The inner jets extend out just a couple of light years from the black hole itself, before gracefully fading away their energy, seemingly dissipating close to their source. But then mysteriously, the outer jets appear far out, some 75 light years from the black hole, and then stretch for an additional 300 light years or so, an astonishing cosmic reach. We still don't quite know how exactly these outer jets form, or why they persist for such an incredible distance before finally terminating after those 300 light years, and we only have a rough idea of what they are even made of, their composition remaining a subtle puzzle. But a recent study from the HESS collaboration, a team of diligent cosmic detectives, has given us some valuable new clues to begin answering these profound questions. One such clue lies in the presence and precise distribution of high-energy photons called gamma rays being emitted by SS 433. Ordinarily, stars or even active accretion disks could not be expected to produce any significant amount of gamma rays simply because their temperatures are far too low, their energies too gentle. But the outer jets streaming from SS 433 unexpectedly seem to emit them in spades a powerful high-energy whisper from the depths of space. What's even more surprising, more delightfully puzzling, is that even though these outer jets are incredibly hot, blazing with immense energy, the spectrum of light they're emitting, the unique fingerprint of their radiation isn't consistent with an ordinary thermal distribution of photons. It's not just heat, but something more fundamental at play. So the quiet question remains, what unseen powerful process is generating all of those high-energy gamma rays? The current leading theory, a beautiful piece of cosmic deduction, suggests that the outer jets contain incredibly high-energy electrons. Electrons that have been accelerated to astonishing speeds. These energetic electrons can then bump into lower-energy photons, passing through the system like a cosmic game of billiards. In these collisions, the high-energy electrons transfer their immense energies to the photons, boosting them into the gamma-ray spectrum. This fascinating process goes by the name of inverse Compton scattering. Imagine a tiny energetic pebble hitting a slow-moving larger rock and instantly transforming it into a high-speed projectile. The scientists at Hess realized that by meticulously measuring the energy of these emitted gamma rays, they could glean a wealth of information about the energy of the electrons in the jets that produced them in the first place. And what they found was in full support of the inverse Compton scattering theory. The highest energy gamma rays, those carrying over 10 tera-electron volts of energy per photon, an astonishing 10 trillion times more energy than a single photon of visible light, were primarily coming from the innermost region of the outer jets, right where they first appear. Gamma rays with lower energies, on the other hand, radiated from correspondingly farther distances down the majestic length of the jets of SS 433. This distribution, this graceful tapering of energy, is a clear indication that electrons further down the jets have less energy to transfer to photons than the electrons right at the beginning of their journey. Or to put it more simply, as these incredibly energetic electrons stream along the outer jets, they tend to lose energy over time, presumably due to their constant subtle collisions with those lower energy photons, slowly, patiently transferring their energy to the surrounding light. It's a gentle deceleration, a cosmic expenditure of energy. But the deeper question remains a quiet hum in the cosmic symphony. How did these electrons acquire such astonishingly large energies to begin with? Models suggest that their initial launch velocity from the black hole itself was just about 1/4 of the speed of light, incredibly fast, but still far from the ultimate cosmic speed limit. Yet by the time they reach the outer jets, these high-energy electrons appear to be moving at speeds greater than 99% the speed of light, an almost unfathomable velocity. This incredible acceleration multiplies their initial energies by a staggering factor of 1 billion. The Hess collaboration believes that this wild, almost magical acceleration occurs due to a powerful shockwave at the very base of the outer jets, a kind of cosmic sonic boom. This shockwave is caused by complicated configurations of magnetic fields, invisible forces that guide and accelerate particles in the cosmos. Imagine, if you will, a cosmic game of Mario Kart, where each time an electron interacts with this shock front, it gains a sudden powerful boost of speed, as if it crossed a hidden boost pad. And due to the intricate diffusion of electrons back and forth within the jet, some electrons can cross over this boost pad again and again endlessly, like an infinite speed glitch in the cosmic race. This continuous powerful process is called diffusive shock acceleration, and it may well be responsible for amping up electrons to energies in the hundreds of tera-electron volts, just enough to be able to produce the incredibly high-energy gamma rays observed by Hess. but shedding light on the intricate production of photons within the outer jets of SS433 is truly just the beginning. Microquasars scattered like rare jewels throughout the vast expanse of our Milky Way hold untold treasure troves of information about the inner workings of even the most massive quasars that blaze at the centers of distant galaxies. They are local models, accessible laboratories, allowing us to understand phenomena that are otherwise too far away to study in such detail. And now that we know to look for them, now that their subtle whispers have been detected, microquasars are less like hidden gems and more like beacons in the night sky, posing patiently for our astronomers to capture their beauty in an entire spectrum of photographs, revealing ever more shocking and delightful surprises with each new observation. So what unexpected truth, what gentle surprise resonated with you from today's quiet contemplation? Was it the possibility of powerful shock waves in the deep silent space near black holes accelerating particles to almost unimaginable speeds? Or was it the humbling yet exhilarating fact that our own Milky Way is home to dozens of these little quasars, of its own miniature cosmic lighthouses twinkling in our galactic backyard? Allow your thoughts to drift with these wonders as you settle deeper into the quiet of the night. Black holes, as we gently know, are the densest objects in existence, with gravity so incredibly powerful that not even light the swiftest traveler can escape their relentless embrace. It comes as no great surprise, then, to find the largest of these cosmic leviathans, the supermassive black holes, nestled at the very centers of galaxies. Here, over billions of years, matter has been steadily fed into them like a cosmic river, flowing into an unseen mouth, continually increasing their immense mass. The very largest of these supermassive black holes can be truly colossal, weighing in at billions of times the mass of our own sun. They are the silent ultimate anchors of their galactic homes. However, and this might come as a quiet surprise to you, some of the most massive black holes we know of are paradoxically also among the youngest. This seems to defy our intuition, doesn't it? Surely the older ones, having had more time to gorge on cosmic material, should be the heaviest. But here's the cosmic trick. When we gaze at truly distant galaxies, we are not seeing them as they are now, but as they were in the deep past. We are quite literally looking back in time, and the galaxies that blaze billions of light years away from us often harbor the largest black holes. If our universe is only a tender 13.8 billion years old, and the light from these distant objects takes billions of years to reach our telescopes, that means the galaxy we are observing can only be a few billion years old at most from our perspective. It's still quite young for a galaxy merely a cosmic infant. Surely, though, it should logically follow that nearer and thus older supermassive black holes would be more massive, seeing as they've had so much extra time to consume matter falling into their gravitational wells. So, what subtle cosmic forces are at play here? What grand narrative explains this apparent paradox? The very largest supermassive black hole we currently know of is known by the rather unassuming name TN 618. Its mass is almost incomprehensible, an incredible 66 billion solar masses. By itself, its sheer mass is comparable to the entire Milky Way galaxy. Yet TN 618 is exceptionally far away its ancient light, taking a staggering 10.8 billion years to reach us. This means we are observing it as it was 10.8 billion years ago, which further implies that it can be at most around 2.8 billion years old from that ancient perspective. By comparison, our own Milky Way galaxy, our familiar cosmic home, is approximately 13.6 billion years old. Yet the supermassive black hole found at our galaxy's core, Sagittarius Eggii, is a mere 4 million solar masses. Even the Andromeda galaxy's supermassive black hole, while larger than ours, is still only 200 million solar masses. The contrast is striking, isn't it? One of the big factors to consider here, one of the subtle complexities, is the inherent difficulty in detecting and measuring black holes themselves. This is still a remarkably new field of research, a frontier of cosmic exploration. Our technology has only just in the last few decades allowed us to begin truly observing these enigmatic objects. Even then, we can often only observe the area surrounding black holes, the luminous maelstrom of matter being drawn into their grasp, rather than the unseen heart itself. That is, until the Event Horizon Telescope came along, allowing us to glimpse the silhouette of a black hole for the very first time. But even that monumental undertaking takes ages to image just one black hole, requiring a global network of telescopes. So our general understanding, our cosmic map of these elusive giants, truly is still quite limited, a work in progress. In fact, most of the distant black holes we know about, the ones that shimmer across the vast cosmic canvas, can only be seen precisely because they are quasars. TON 618. That colossal example is indeed a quasar. This means that matter is pouring into its accretion disk at an incredible, almost incomprehensible rate. And because of this torrent of infalling material, it has erupted into a quasar, blazing with energy across the cosmos. Quasars, you see, can only be sustained for as long as matter is relentlessly falling into them. Otherwise, they revert back to being quiet, dark black holes, their immense power unseen. It is truly hard to fully grasp the intricate physics of the accretion disk, that swirling whirlpool of superheated matter. But it is profoundly believed that the friction within these disks is so immense, so incredibly powerful, that the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. Imagine a single point of light outshining a billion suns. TON 618, in its blazing glory, produces as much light as 140 trillion suns, completely outshining the galaxy it resides in, to the point that we can't even see the host galaxy itself from our vast, distant perspective. Its brilliance is a cosmic veil hiding its own home. However, precisely, because quasars are the brightest objects in the universe, they possess an inherent advantage: they can be seen from very, very far away. So one compelling reason for this apparent paradox of large black holes being far away is down to something known as Malmquist bias. Imagine trying to count all the lighthouses in the world from a single distant ship. You would naturally see the brightest, most powerful lighthouses stretching far across the horizon, appearing plentiful. But you would inevitably miss the smaller, dimmer lighthouses much closer to shore, simply because their light doesn't travel as far. This is the cosmic equivalent. Brighter objects further away appear more plentiful in our observations, when in reality, we simply can't see the dimmer objects at that distance. This implies there may well be a compelling argument that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. We just haven't found them all yet. If a galaxy has a very large black hole, but it's not an active quasar, it means we won't see it after a certain distance, because a galaxy, even a grand one, is far, far dimmer than a blazing quasar. Another profound reason why we don't observe the biggest black holes close to us is due to the very nature of the universe itself, particularly in the epoch shortly after the Big Bang. As you may gently know, the universe is not static. It is ever expanding continuously, stretching and growing. And during the early universe, matter was a lot closer together, densely packed, like a cosmic soup. Quasars were far more common back then, a natural consequence of the chaotic, energetic early universe. They need extreme amounts of matter falling into them to give off light, and there was simply a lot more loose gas available during the early stages of the universe, waiting to be consumed. Not only has the universe expanded, stretching matter thinner across the vast distances, but over immense spans of cosmic time, gas, that fundamental building block, gets continuously converted into stars. And some of the largest types of stars in their dramatic final acts eventually turn into neutron stars and black holes themselves, meaning that this gas never gets recycled back into the readily available fuel that can fall into a supermassive black hole. Less available gas means, quite simply, less gas will fall into a supermassive black hole. It's a natural consequence of cosmic evolution. One of the theories for the ultimate fate of the universe is actually based on this very principle, a concept called the Big Freeze or heat death. This theory posits that after some trillions of years, all the gas in the universe will eventually be converted into stars, which will then, in their own time, become black holes. The universe will become a cold, dark place, devoid of new light. Even now, we see some galaxies where their gas has been completely used up, consumed entirely, meaning no new stars can form. These are the elliptical galaxies, those serene, ancient cosmic cities. Spiral galaxies, on the other hand, still possess their vibrant gas and dust structures, and thus can still produce new stars, a continuous gentle creation. It is interesting to note that most of the largest supermassive black holes appear to be nestled in elliptical galaxies, precisely where there is no more gas left to form new stars. This suggests a profound connection. Gas needs to lose its momentum, its angular momentum, to fall into the galaxy's central supermassive black hole. And if that has already happened, if all that gas has already been efficiently funneled inwards, then the supermassive black hole is likely to be much, much bigger because of all the infalling matter it has consumed. With elliptical galaxies, this process of gas infall and consumption has largely completed, resulting in their vast, quiet centers. Whereas with spiral galaxies, this hasn't happened to the same extent. They still retain their swirling reservoirs of gas and dust. One such powerful trigger for gas to lose its angular momentum to begin its inward journey could be the gravitational influence of nearby galaxies or even dramatic collisions with other galaxies. These cosmic encounters can stir up gas, creating shock waves and gravitational tides that strip the gas of its momentum, sending it spiraling towards the galactic core. In addition, as we've noted, there is simply less gas available in the universe now than there was during the wild, chaotic early universe. So black hole growth, that immense cosmic feeding, probably occurred much more rapidly back then in the universe's energetic youth, but has significantly slowed down now. This might be precisely why there is no blazing quasar within 500 million light-years of us, no cosmic beacon outshining its galaxy in our immediate cosmic neighborhood. As the universe ages, as things become less chaotic and more spread out, the number of active quasars has naturally decreased, their fuel sources dwindling, which means that the only quasars we see, some of which host the largest black holes we know of, are those whose light has traveled for eons, reaching us from a time long, long ago when the universe was a far more energetic and dramatic place. So why are the largest supermassive black holes often observed as the youngest? Well, although it may appear that way, a beautiful paradox in itself, it might not actually be the case at all. It is more likely a subtle trick of perception combined with the universe's own evolving nature. We can easily measure distant bright quasars simply because we can see them, their light blazing, across billions of light years. Older and closer black holes may also be immensely large, perhaps just as large as those distant quasars. But because of Malmquist bias, that subtle cosmic blind spot, we simply haven't found them yet. They are dark, silent giants waiting to be unveiled. As studies continue, as our technology improves, and as new cosmic eyes, like the James Webb Space Telescope, continue to gaze deeper and more clearly into the universe, we will slowly, patiently, start to get a more complete and nuanced picture of the universe around us. We will find those hidden giants, those silent behemoths, and unravel more of the universe's grand quiet truths. It is a journey of endless discovery where every new piece of light, every subtle whisper from the cosmos brings us a little closer to understanding our place in this magnificent, ever-evolving tapestry. With the James Webb Space Telescope now gazing upon the cosmos, I felt it would be a gentle idea to revisit some of the remarkable images captured by its magnificent predecessor, the Hubble Space Telescope. Hubble, our venerable eye in the sky, has graced space for over 30 years now. tirelessly expanding our understanding of the universe drastically during this profound span of time. It has been a steady, unwavering guide, showing us wonders we could only dream of. One particular type of object Hubble has observed with exquisite detail are galaxies. Galaxies, as we've seen earlier in this quiet journey, come in all different shapes and sizes, from delicate luminous smudges to colossal sprawling cities of stars. Their star populations can range from a mere few million to the astonishing trillions. They are truly fascinating, beautiful objects, each one containing its own unique story of how it formed the way it did, a testament to the myriad paths of cosmic evolution. And within each, there lies the tantalizing whispered question about the possibility of life, perhaps in some distant solar system, nestled within their star-studded embrace. While we have only observed the tiniest fraction of the total number of galaxies in the observable universe up close, imagine trying to count all the leaves in a forest by looking at only a handful. Did you know that Hubble has seen galaxies all the way through their evolution? From galaxies in the very throes of starbirth, blazing with the energy of creation, to those majestic but quiet starburst galaxies, to galaxies that are now inert, anemic, or slowly, gracefully dying. Each image a chapter in the cosmic epic. I invite you to join me today as we gently look through this spectrum of galaxy evolution, focusing particularly on the ghostly, beautiful remnants of galaxies that are in their own profound way on their way out. These are the quiet sunsets of cosmic life, beautiful in their own unique way. I hope by the end of this quiet contemplation to have earned your gentle appreciation and perhaps your continued journey with us. When we gaze upon a galaxy, one of the first most telling indicators of its stage of evolution is simply its shape. It is generally believed that spiral and bar galaxies represent some of the least evolved galaxies in the universe, still brimming with the raw materials for new life. These are the cosmic nurseries full of potential. Conversely, elliptical galaxies are considered the most evolved, having long since settled into a serene, often quiet existence. That doesn't necessarily mean that spiral and bar galaxies are intrinsically younger in age. It's simply that they take a much longer, more active path to evolve into their final, calmer forms. They are like grand old trees that continue to bear fruit, while ellipticals are the ancient oaks that stand tall and majestic, their fruiting days long past. Here, for example, is number 68 NGC 2336. Gaze upon its graceful form. Galaxies with spirals consist of flat, elegant disks, where stars mainly orbit in the same gentle direction, a cosmic carousel of light. One of their most defining characteristics, of course, are those beautiful arms that extend majestically from the galaxy's center. These arms can spiral out directly from the galaxy's core, or sometimes with a touch of added complexity, the spirals might gracefully emerge from a central bar of stars. They are concentrations of stars, certainly, but crucially also of gas and dust. A galaxy that boasts an abundance of this cosmic dust is a gentle whisper that it is likely not as far along its evolutionary path as less dusty galaxies. This is because this precious dust has yet to be fully converted into new stars, its potential still largely untapped. Should no external influence accelerate this cosmic consumption, a galaxy like NGC 2336 may continue to produce stars at a fairly slow but wonderfully steady rate for billions of years yet. It is a slow, enduring act of creation. How do we know it's not producing stars very quickly, like a frenetic workshop? Well, a distinct feature about this galaxy is the noticeable lack of vibrant red H-I regions, those blazing stellar nurseries, those hotbeds of new birth. Instead, while star formation is clearly still taking place, evidenced by all the bright blue stars you can gently discern in this image, it will remain as a spiral galaxy for a much longer time than a galaxy blazing bright with numerous H-I regions, which speaks of a more frantic pace of birth. Now let your eyes drift to number 69 NGC 972. Wow, what a pretty galaxy, isn't it? It almost looks like it's ablaze, shimmering, with an intense inner fire with all the activity happening around it. When a galaxy glows with such a vibrant red hue, we characterize it as a starburst galaxy. That is to say, star formation, the profound act of creating new suns, is happening at an incredibly rapid, almost frantic rate. These intensely red regions are precisely the HII regions, those glowing nurseries of ionized hydrogen that the previous galaxy was so noticeably lacking in abundance. They are the fiery cradles of new life. As this starburst continues this furious pace of creation, it will swiftly use up the vast gas and dust structures you can see here, consuming it all, converting every last wisp into the brilliant points of new stars. Also notice the ethereal blue glow, almost like a halo around the galaxy. This captivating blue hue emanates from blue stars, which are the hottest, most massive, and most luminous star types. Their presence is another clear indicator of rapid star formation, as these majestic yet short-lived stars require immense amounts of matter to fall into them during their formation. They are born in a blaze of glory and live incredibly fast, luminous lives. Consider next number 70, Messier 61. Another incredible, almost breathtaking example of a starburst galaxy. M61 is a particularly fantastic galaxy for observation, for it is angled almost exactly face-on to us, offering a clear, unobstructed view of its intricate beauty. This perfect alignment means that all its delicate dust lanes and its fiery red nebulae can be studied in exquisite detail. That's a lot harder to do, of course, with a galaxy that is angled edge-on, where its internal structures are compressed into a thin line. Looking closely at the very center of the galaxy, your eye might catch a neat symmetry in the swirling dust lanes, a sense of cosmic order. However, the further out you gently zoom, the more you begin to notice how this symmetry gradually becomes less perfect, less pristine. This arm, for example, seems to split into 3 distinct pathways, whereas its counterpart retains its more coherent, singular structure. Usually, an asymmetrical galaxy whispers a story of disturbance, indicating that it is being perturbed in some way. This might be from the subtle yet powerful gravitational influence of a nearby galaxy, its unseen hand tugging at the cosmic fabric, or from an actual ongoing collision with another celestial body. In this particular case, M61 is found approximately 50 million light-years away, nestled right in the heart of the vast Virgo cluster, a colossal gathering of over 1,000 galaxies. It is precisely this outside influence, this constant gravitational interaction with its numerous cosmic neighbors, that is likely causing the intense starburst activity within M61. This external tug of gravity causes the diffuse dust clouds within the galaxy to gently collapse in on themselves, triggering the rapid birth of countless new stars and accelerating the galaxy's evolution, a dramatic, beautiful transformation under external influence. All galaxies in their long and majestic lifespans will eventually exhaust their precious supply of gas and dust. These fundamental building blocks are continuously converted into stars, which, in their own time, will eventually evolve into denser, more compact forms like neutron stars or black holes. A small but significant percentage of this gas and dust also gets consumed quietly, devoured by the supermassive black hole, believed to exist at the center of every sizable galaxy. It's an inevitable slow expenditure of resources. What then happens to a galaxy once its wellspring of new creation begins to dry up? Well, NGC 4921 offers us a compelling example of a galaxy that is on the very cusp of transitioning into what is known as a lenticular galaxy. However, as you can still gently discern this, one still has its distinctive spiral arms, visible, though perhaps a little faded, a little less vibrant. So for now, it remains classified, if only provisionally, as a spiral galaxy. It seems that the ongoing process of star formation and the presence of those distinct dust lanes are key elements, crucial ingredients in maintaining the beautiful flowing shape of a spiral galaxy's arms. And when this vital process stops, when the raw material finally runs out, the arms, like a fading dream, seem to lose some of their sharp shape and definition, blurring softly at the edges. The very color of the galaxy also subtly changes, shifting from the vibrant blues of youth to a ghostly white or a soft reddish white, as the galaxy's population of hot, short-lived blue stars gradually burns out and fades from existence. This particular galaxy, NGC 4921, is truly fascinating. It is really unusual, almost poignant, to witness a spiral galaxy so profoundly devoid of its usual vibrant color. The only colors truly visible are the few remaining blue stars, like tenacious sparks still clinging to the last vestiges of the dust lanes, a quiet testament to a fading process. Astronomers have affectionately, yet somewhat sadly, described this galaxy as anemic for star formation. Here must be incredibly slow, a mere whisper compared to the roaring fires of a starburst galaxy. It is a slow, graceful descent into a quieter, more subdued existence. Now let us turn our gaze to number 72 NGC 2217. This is in truth the first genuine lenticular galaxy I've shared with you today. Notice its quiet beauty. Although NGC 2217 isn't totally done with star formation just yet, you can still discern the faint shimmer of blue stars, like tiny hopeful embers, around the outer edge of the galaxy. It is clearly in a transitional phase. However, in this instance, the dust, that vital building block, is almost completely exhausted, its reserves depleted. And the once vibrant spiral arms have lost their definition, their graceful curves now blurred into a softer, less distinct form. The prominent bulge at the center of the galaxy glows with a serene white and reddish hue, clearly showing that only older and less massive star types, those long-lived enduring suns, now exist here. There are no vibrant blue stars visible to speak of in its core, only the quiet glow of age. Let your eyes drift to number 73, PGC 1922. Here's another beautiful face-on galaxy for your contemplation. This particular lenticular galaxy is even further along its subtle journey of evolution. Most of the galaxy here is completely devoid of gas and dust, a truly empty cosmic canvas, apart from a faint concentration towards its very center. You'll also notice how any arms that might have once existed, those graceful spirals, have been totally wound up like a cosmic spool until they are almost indistinguishable, utterly lost in the uniform glow. All that's left, truly, are old stars and a remarkably flat disk, a testament to a quiet, settled existence. But even this flat disk will eventually lose its shape as the galaxy gently widens and evolves into a full-fledged elliptical galaxy, its final serene form. We can see this very process of subtle transformation unfolding with number 74 NGC 1947. With this lenticular galaxy, we can still discern the wispy faint remnants of its former spiral arms, like ghostly memories of a vibrant past. However, the stars in this galaxy have clearly already stopped orbiting, predominantly along a flat disk, their individual paths now more varied and chaotic. Instead, they simply orbit slowly and from all directions, a gentle, almost random dance, losing the cohesive flow of a spiral. The very last stages of a lenticular galaxy often look something like NGC 1533. Here, there's no gas or dust noticeably present its resources long depleted. However, you can just about see the faint lingering remains of a bar structure coming away from its core. A subtle, almost imperceptible hint indicating that this quiet galaxy was once in its distant youth, a vibrant bar spiral galaxy. Eventually, what you end up with, the grand quiet culmination of this evolutionary journey, is something like number 76 Messier 105. This is a true elliptical galaxy, a galaxy almost totally devoid of gas and dust, a cosmic desert where new life no longer blossoms. This galaxy is so remarkably anemic so utterly quiet in its star formation that only one sun-like star is produced in a galaxy like this, approximately every 10,000 years, a mere flicker of new light in vast eons. So what you are left with is the vast majority of the stars found in this galaxy being older, redder star types, their youthful blue glow long faded. If we were to gently zoom into this image, you would begin to discern the faint red sprinkling of these ancient stars, especially as we move away from the blinding brightness of the galaxy's core. This is the last stage of a galaxy's evolution, that we can truly observe a serene, settled end. These long-lived stars will continue to last for billions to trillions of years, their light slowly dimming. And our universe in its own grand youth is still too young to see what happens eventually to a galaxy like this, though it is thought that they will simply become dimmer and dimmer, fading into the cosmic twilight as one by one their ancient stars finally reach the quiet end of their incredibly long lives. So there we have it, a quiet snapshot of the majestic slow-motion evolution of galaxies. While having an almost spooky, ethereal vibe to them, I find lenticular galaxies particularly captivating. Their unstable transitional nature truly produces some amazing patterns, some delicate fleeting structures that you simply can't find in any other galaxy type. Although it is somewhat sad to gently consider, too, that as the universe ages, as eons unfold, vibrant spiral galaxies will inevitably become less and less common, their dynamic beauty slowly fading until the only galaxy type remaining in the cosmic tapestry are the serene, ancient elliptical galaxies, scattered like quiet luminous islands in the deepening cosmic night. Hubble, our faithful companion in the sky, has generously released a zip file on its website containing what it considers its top 100 most breathtaking pictures ever taken. What I will quietly endeavor to do over the course of this series is to gently go through these magnificent pictures one by one and explain with quiet contemplation what it is you're truly looking at. And believe me, some of these pictures require a gentle guiding explanation, for their secrets are deep and profound. Let us now turn our gaze to number 22 NGC 4449. At first glance, my quiet thoughts drifted to one of the Magellanic Clouds, those familiar companion galaxies to our own. But this is in fact a small yet remarkably active irregular galaxy nestled within a larger galaxy group called Canes Venatici, approximately 12 million light-years away. This means, like us, it is part of the vast Virgo supercluster, also known as the local supercluster of galaxies, a grand cosmic neighborhood. It shares a general bar shape with the large Magellanic Cloud, our well-known galactic satellite. But the profound difference lies in its classification. This is considered a starburst galaxy, a vibrant, bustling nursery of new suns. It is incredibly active in producing new stars, a furious cosmic engine of creation, as can be clearly seen in those beautiful pinkish regions. Pink or red areas within a galaxy are generally a telltale sign, a luminous whisper of intense star formation. Here, vast clouds of hydrogen gas are ionized by the fierce energetic radiation from newly born massive stars, causing the hydrogen to glow with that characteristic vibrant red hue. It's like a cosmic blush, signifying life. Another unmistakable sign of high rates of star formation is the multitude of bright blue stars that shimmer throughout this picture. Blue stars, as we've gently explored, are extremely hot, incredibly young, and often immensely massive. They burn through their nuclear fuel at an astonishing rate, living incredibly fast, luminous lives, and therefore burning out quickly. Because these stars can only live to a certain age, a cosmic fleeting moment, their abundant presence tells us with quiet certainty that they must have only been produced within the last few million years. And as we can clearly see, there are many clusters of these dazzling blue stars scattered across this galaxy, each a testament to a recent powerful wave of creation. This intense starburst activity in NGC 4449 is thought to be because of other galaxies subtly interacting with it. Imagine a gentle gravitational dance where the unseen tugs from neighbors stir the cosmic dust and gas. If we zoom out a bit, our eyes might catch a faint trail of red stars, almost like a celestial breadcrumb trail. Perhaps these are the remains of a spheroid galaxy, a smaller, quieter companion that once passed through NGC 4449. Its form stretched and distorted by this powerful tidal effect, leaving behind a ghostly, luminous wake. Looking closely at the galaxy's center, we see a bright white group of stars, a luminous core surrounded by some dark, intricate clouds of dust. These very clouds are where new stars can form, patiently waiting for the right conditions to collapse and ignite. This energetic galaxy, vibrant with new life, spans a breathtaking 19,000 light-years across. Now let us turn our gaze to number 23 HD 97950. This truly spectacular superstar cluster is found nestled within NGC 3603, a colossal HII nebula. It is incredibly pretty, a vibrant tapestry of light and gas, and has been studied a great deal because of its prime location. It's found in the Carina spiral arm of our own Milky Way, roughly 20,000 light-years away. NGC 3603 is particularly interesting to astronomers because it holds the distinction of being the most massive visible cloud of glowing gas and plasma known as an HII region in the entire Milky Way. And the superstar cluster within it, HD 97950, boasts the densest concentration of stars known in our galaxy, a truly packed cosmic city. The intense ultraviolet radiation and powerful stellar winds streaming from the massive young stars within this cluster have over eons meticulously carved into the surrounding dust, pushing it away, shaping it into these beautiful, intricate forms. This cosmic sculpting has also serendipitously given us an unobscured view of the superstar cluster itself, allowing its inner brilliance to shine forth. Stars of note within this bustling cluster include Cher 25, a majestic star weighing in at 60 times the mass of our Sun, and in its luminous life, reaching the very end of its life cycle. It is expected to go supernova any time now, a final spectacular blaze of glory, as it has already gently thrown off matter in a manner similar to what has been observed in other stars preceding a supernova. We also find the three main stars at the very heart of the cluster. Barely distinguishable, their individual forms, almost blending together in the intense brilliance of these images. All three are Wolf-Rayet stars, each a colossal cosmic furnace about 100 times the mass of the Sun and millions of times more luminous. Two of them are incredibly close together, locked in a tight embrace as part of a binary star system taking only 3.5 days to orbit one another. This means they are practically touching, no doubt, constantly exchanging vast amounts of mass, as well as exerting an incredible tidal influence on each other. A dramatic, intimate, cosmic dance. Zooming out a bit, we see that visually, NGC 3603 appears right next to another beautiful nebula, NGC 3576. But in actual fact, this other nebula is much closer to us, only about half the distance. They just so happen to be visually aligned, a beautiful trick of cosmic perspective. Now let us float towards number 24, Messier 74. On first glance at this image, my mind immediately thought of another famous galaxy we've already had the quiet pleasure of contemplating, the Whirlpool Galaxy. And indeed, placing them side by side, these two galaxies do look remarkably similar, like cosmic siblings. They are both grand design spiral galaxies for a start, their arms elegantly unfurling with a striking clarity. And they share similar dust patterns, those intricate dark lanes weaving gracefully through their luminous arms. But placing them side by side, you can discern the subtle variations, the unique characteristics that distinguish these two cosmic beauties. M74's arms are generously lined with hot, bright blue stars, each a recent birth with vibrant pink and red star-forming regions dotted all over like scattered jewels of creation. You may instinctively think that the arms of galaxies like this are static, rigid structures rotating uniformly around the galaxy's nucleus, like the spokes of a wheel. But as we've gently discovered, that's not quite right. They are, in fact, the luminous visual effect of density waves. As gas and dust and even existing stars patiently orbit the galaxy's core, they pass through these subtle yet powerful density waves. This gravitational compression causes the gas and dust to clump, to become denser, and crucially, to trigger the birth of new stars. Existing orbiting stars also naturally clump up in these density waves, creating the illusion of the solid arm. A great many of these newly born stars will be those short-lived, brilliant blue stars, perhaps completing their entire life cycle in only a few million years, a mere blink of an eye in cosmic time. M74 is situated approximately 32 million light-years away from us and possesses a relatively low surface brightness, making it one of the most difficult Messier objects for amateur astronomers to observe, which has earned it the rather evocative nickname, the Phantom Galaxy. It is probably just a little smaller than our own Milky Way galaxy, containing about 100 billion stars and spanning a vast 95,000 light-years across. It peacefully resides in the M74 group, a small, somewhat remote cluster of galaxies drifting through the cosmic currents. Let your gaze now fall upon number 25 ARP 148. So first impressions. My curious friend, what do you think this could possibly be? Allow your imagination to wander freely for a moment. Well, this truly bizarre shape, found a staggering 500 million light-years away, is in fact a galaxy, and it has been nicknamed Mayle's object. It is most likely two galaxies in the very act of merging a profound cosmic embrace. The initial collision, the moment of impact, is theorized to have created a powerful shockwave that dramatically drew matter into the center of the combined system before it propagated outward, rippling into this remarkable ring shape. You can still see the faint tail, a luminous streamer of stars from one of the galaxies, further suggesting that this is an ongoing dynamic collision, a cosmic dance of destruction and creation. Interestingly, and on a little side note, the ARP catalog is appropriately the Atlas of Peculiar Galaxies, a collection of cosmic oddities and marvels. Now, if you thought the last image was an impressive distance away, prepare to be humbled by the next. Have a look at number 26 Abel 2218. This is an incredibly impressive cluster of galaxies located a staggering 2.1 billion light-years away. Clusters like these vast gatherings of galaxies, are particularly scientifically interesting because their immense collective gravity subtly bends the light around them, acting as a colossal magnifying glass in space. This phenomenon, known as gravitational lensing, allows us to see galaxies that are even further behind them, objects that would otherwise be entirely invisible to our telescopes. Those long ethereal arcs you see in the image are not separate objects, but are actually the light from incredibly distant galaxies stretched and warped by the powerful gravity of the nearer galaxy cluster. Imagine looking through a distorted glass where distant lights are smeared and elongated. In this particular image, we can glimpse perhaps the most distant galaxy known at the time it was captured, estimated to be an astonishing 13 billion light-years away. In the raw image, it's barely visible, a mere whisper of light, but in an enhanced version, its stretched appearance becomes more discernible. Because of this powerful lensing effect, the galaxy appears twice in this single image here, as well as here, a twin cosmic ghost. We see its ancient light from Earth, as it was only 750 million years after the Big Bang, meaning we're truly looking back in time to the very early universe, witnessing its nascent form. This single image, a window into the deep past, contains around 10,000 galaxies each, a universe of its own. Let your gaze drift to number 27 Abel 1703. This is another magnificent galaxy cluster, performing the same incredible lensing effect we just contemplated. I want to gently explain in a little more detail how this subtle yet powerful gravitational lensing effect truly works. Firstly, we begin by observing a distant massive object, often a vast galaxy cluster. Gravity, as theorized by Albert Einstein, profoundly warps space-time itself. Perhaps a topic we will gently explore in another quiet contemplation. But it is worth noting here that often elliptical galaxies with their immense mass are the biggest galaxies in existence. And the more massive the galaxy, the greater, the more pronounced the warping effect it has on the fabric of space-time around it. You can clearly see this profound effect with the lensing around the large elliptical galaxy situated right in the middle of this image. As space-time itself is warped, the path of light, that swift cosmic messenger, is gently bent around the massive galaxy. And if by a stroke of cosmic alignment, a distant galaxy happens to be positioned just right directly behind this gravitational lens, it gives us a magnified view of the other side of that distant galaxy, a truly unique perspective. It acts as a natural, incredibly handy magnifying glass, floating effortlessly in space, revealing what would otherwise remain hidden. And about this specific galaxy cluster, Hubble 1703 is located approximately 3 billion light-years away, its gravitational power bending light across unimaginable distances. Space, in its boundless mystery, can be truly beautiful. You have those seemingly flawless elliptical galaxies, those serene cosmic cities with no traces of dust bands to block the view of their stunning smooth shape, a quiet perfection. You have grand majestic galaxies with spiral arms that gracefully wrap around the entire galaxy with a surprising level of symmetry, an intricate cosmic dance. And then there is the ARP catalog, the Atlas of Peculiar Galaxies, a collection of cosmic rebels. These are galaxies which in their beautiful chaos laugh in the face of conventional order. They are often going through a very tumultuous time in their existence, dramatic periods of transformation. And they are fantastic in their own right, each a unique, compelling story to tell. I invite you to join me on this quiet journey as we gaze upon some of the most peculiar galaxies that Hubble, our venerable eye, has ever seen, and I will try to gently explain what it is you are truly looking at, what cosmic drama is unfolding before our very eyes. Let us begin with number 43 ARP 116, also known as Messier 60. At first glance, this galaxy doesn't seem so unusual, does it? It appears to be a standard elliptical galaxy, a massive cosmic city, which has already used up most of its dust and gas in creating stars, which gives it that characteristic smooth, serene appearance. It can be found 57 million light-years away and harbors one of the biggest black holes ever discovered near its center, an immense entity, roughly 4.5 billion solar masses. But this isn't particularly peculiar so far, is it? Zooming out just a little bit reveals something truly very unusual, a subtle cosmic twist. M60 is situated right next to another very different-looking spiral galaxy called NGC 4647. From our distant viewpoint, it certainly looks as though these two galaxies should be actively interacting with each other, their gravitational fields tugging and pulling. But surprisingly, there aren't any immediate signs of this, no obvious warping or distortion of their graceful forms. This is truly very unusual to see two galaxies in such close cosmic proximity, yet without any apparent gravitational dance or twisting of their shape. As it turns out, they are not side by side engaging in a cosmic waltz. Instead, one is simply positioned in front of the other from our earthly perspective, a beautiful trick of cosmic alignment. But there's one other truly unique thing nestled within this image, another galaxy you probably haven't noticed, a tiny, almost invisible presence. This tiny little galaxy, a mere cosmic speck here, is known as M60 UCD1. It holds the remarkable distinction of being the most densely packed galaxy that we currently know of. Despite being only 300 light-years across a mere cosmic whisper in terms of size, it remarkably contains 200 million solar masses compressed within its tiny embrace. Towards the very center of this tiny galaxy, stars are so incredibly densely packed that it makes the density of stars about 15,000 times greater than what is found in Earth's own neighborhood within the Milky Way. This means that the stars are about 25 times closer together than our own sun's companions, truly a crowded cosmic metropolis. An X-ray view of the surrounding area, captured by the Chandra telescope, reveals all the black holes and neutron stars found in Messier 60 like hidden cosmic embers. And as you can clearly see, this tiny galaxy, M60 UCD1, also possesses a powerful X-ray source, strongly indicating the presence of a black hole at its very center. Scientists believe that this is a black hole with roughly 10 million solar masses, which remarkably would make it just a bit bigger than the black hole found at the center of our own Milky Way galaxy. If this is indeed the case, it is thought that this tiny galaxy used to be much, much bigger, a far grander cosmic entity, but most of its mass was dramatically stripped away by powerful tidal forces, leaving behind just this incredibly dense cluster of stars found near its powerful compact center. Now let us turn our gaze to number 44 ARP 147, also known by its other designation, IC 298. You don't have to look too closely at this image to immediately determine that this is a truly very weird-looking galaxy, a cosmic anomaly that catches the eye. It is in fact a pair of galaxies that have profoundly collided found roughly 440 million light-years away. Imagine two cosmic entities, once separate now, locked in a slow-motion embrace that reshapes their very being. This is precisely what the previous galaxies, those we gently contemplated earlier, could end up looking like if they were ever to collide a glimpse into their possible future. Here, the left galaxy is an elliptical galaxy, its smooth form representing ancient calm, and the one on the right is a spiral galaxy, a dynamic swirl of stars and dust. The collision, estimated to have happened approximately 40 million years ago, created a dramatic consequence. It caused the spiral galaxy to undergo extreme star formation, blazing with new life seen vividly in the bright blue regions. This intense period, this most active time of star formation or starburst, occurred about 15 million years ago. Such a furious pace of creation would have produced the most massive types of stars, those that live fast and burn brightly. But due to these stars being incredibly short-lived, lasting only tens of millions of years, most of the biggest ones have already died, exploding in spectacular supernovae and gracefully transforming into either dense neutron stars or elusive black holes. This reddish part of the ring, a luminous echo, appears to be the original nucleus of the spiral galaxy, now just a segment of the grand luminous ring formed by the collision. Due to elliptical galaxies having exhausted most of their supply of dust and gas star formation isn't nearly as prevalent in the elliptical galaxy in this pair, its quiet core remaining largely unchanged. What you can see, though, is the powerful effect of tidal forces causing a ripple, a kind of shockwave, to propagate through the elliptical galaxy, which you can discern as the stars have gently clumped into distinct rings, a testament to the gravitational violence of the encounter. Now let our contemplation drift to number 45 ARP 77, also known as NGC 1097. Here is another galaxy with a smaller galaxy tucked away subtly inside its embrace, a cosmic secret. Unfortunately, the Hubble image in its focus cuts the smaller galaxy out of its frame. But the European Southern Observatory's ESO, Very Large Telescope, has also had a deep look at these galaxies, and in its view, you can clearly see its smaller neighbor, NGC 1097a, a small elliptical galaxy that is in close orbit around the bigger spiral galaxy. NGC 1097 itself, with its striking central feature, looks quite like a giant eyeball to me, its luminous pupil surrounded by a bright fiery iris. Zooming in on this captivating iris, we can see that it is in fact a ring rich in star-forming regions, each a cradle of new life. Each of the bright blobs, those luminous points within the ring, are thought to be hot bubbles of hydrogen, where new stars are actively forming, blazing with the energy of creation. Viewing different wavelengths of light, those unseen cosmic frequencies, shows that some dust from these vibrant rings is also being subtly sucked in, drawn towards the supermassive black hole found at the galaxy's very center, a slow, inevitable gravitational descent. But this isn't the most peculiar thing about NGC 1097. zooming all the way out reveals something truly extraordinary. 4 distinct jets emanating from the core of the galaxy, arranged in an elegant X shape. Due to the surprising lack of hydrogen gas found within these jets, scientists believe that they are the quiet, luminous remains of a smaller galaxy, that NGC 1097 in its grand slow-motion feasting cannibalized in the distant past. It's a powerful whisper of galactic consumption. Let your quiet attention fall upon number 46 ARP 142. Here is yet another magnificent galaxy merger, a cosmic dance that at first glance kind of looks like a penguin and an egg, a charming, unexpected visual. When viewed like this image might seem serene, almost peaceful in its unique configuration. But in truth, the biggest spiral galaxy in this pairing has taken a considerable beating from this profound merger. That long section you see here stretching gracefully is where one of the spiral arms of the galaxy has been dramatically ripped away by the elliptical galaxy, its immense gravity tearing at the cosmic fabric. The elliptical galaxy, meanwhile, doesn't look too fazed by this colossal collision, other than the fact that it appears quite oblong in shape, its form slightly distorted by the gravitational embrace. Again, those vibrant blue regions along the edges here indicate intense starburst activity, the furious birth of new stars. And this 3D view, a layered perspective, gently shows that these delicate dust lanes are probably becoming detached from the galaxy, too slowly drifting away into the cosmic void. These galaxies caught in their dramatic dance are found roughly 350 million light-years away, their light taking eons to reach our patient eyes. Now let us turn to number 47, R2110, also known as NGC 1469. I don't think you've seen a galaxy quite like this one before, have you? Well, that's because this tiny galaxy, no bigger than the Large Magellanic Cloud gracefully orbiting our own Milky Way, is pretty much just one giant nebula. Imagine a single vast glowing cloud pregnant with the promise of future suns. This galaxy is almost the total opposite of an elliptical galaxy in its essence, as it is incredibly rich in gas and dust that has not yet formed stars. Its potential is still largely unrealized. NGC 1569 is found near the Maffei group of galaxies, a gathering of cosmic neighbors. And due to its close proximity to these much bigger companions, the gas and dust within it has recently been dramatically compressed, creating powerful shock waves. This compression has caused rapid starburst at a rate 100 times faster than anything observed in our own Milky Way, a truly furious pace of creation. Towards its center, blazing with intense light, are densely packed massive stars. These colossal suns have, through their powerful solar winds and spectacular supernova explosions, blasted away the red dust and gas towards the outskirts of the galaxy, clearing their immediate surroundings and leaving behind huge glittering star clusters. The small white stars found in the halo of the galaxy are older stars, those that have been around for much longer, enduring the dramatic changes around them. We can have such a detailed look at this tiny galaxy because although it is small, no bigger than 6,000 light-years across, it is also reasonably close to us at only 11 million light-years away, making it an accessible cosmic laboratory. Finally, let us finish our quiet contemplation with one more extraordinary galaxy merger. Number 48, R272. Seen from a rather interesting, almost poignant angle. These two galaxies caught in a profound cosmic embrace are roughly the same size and are just astronomical moments away from impacting each other, their grand structures poised for a dramatic fusion. There's also a third galaxy found just above them, a silent witness which is also subtly in on the action, its gravity part of the larger dance. The reason for seeing three galaxies merging at the same time, this rare cosmic ballet, could be due to the fact that this is happening within the vast Hercules supercluster, roughly 500 million light-years away. This supercluster is one of the biggest filamentary structures of galaxies that we know about in the universe, a colossal cosmic web. You see, the observable universe, as far as we can tell, kind of looks like a giant intricate web, its luminous threads stretching across unimaginable distances. In this grand design, galaxies often band together drawn by gravity to form these vast filaments, which in turn form the luminous boundaries between colossal empty voids in the universe. This is what the universe up to 500 million light-years from us looks like, a vast interconnected tapestry. And even in this immense space, you can discern this subtle banding of galaxies, these threads of light. And just because some of you have quietly asked about this in the past, this is precisely where Bode's void is, one of the biggest voids of galaxies that we know about, a vast, quiet emptiness in the cosmic web. Thank you for joining me on this gentle journey through the cosmos as we explored the hidden depths and quiet mysteries of our universe. Making this video, these quiet contemplations, required some long-term planning and dedicated work, which we were only able to do thanks to the unwavering consistency and kind sustainability of your memberships as astronauts on Patreon. A huge heartfelt thank you to everyone who has so generously signed up, enabling these explorations. And if you'd like us to make more videos like this to continue these quiet cosmic voyages, you can join us through the link provided. When you join, you'll be able to watch the whole video ad-free, see your name gently acknowledged in the credits, and even submit your own thoughtful questions to our dedicated team. Meanwhile, please feel free to click the link to this playlist for more Astrum content, more quiet whispers from the stars. I'll see you next time under the vast enigmatic sky.